Hello AraaTech viewers, welcome back to another presentation. Today we are diving into the world of machine learning engineering. Our goal is to make this topic understandable for everyone, whether you are new to it or just interested in artificial intelligence. In this presentation, we will cover everything from the basics to advanced techniques. We will show you how machines are trained and how they make decisions and solve problems. We will also discuss how data and algorithms work together to understand situations and make the best possible choices. Thanks again for tuning in. Don't forget to subscribe, like, share, and leave your comment below. Let's start our topic. A machine learning engineer is a professional who designs, develops, and implements machine learning algorithms and models to solve complex problems and make predictions based on data. This role typically involves a combination of skills from computer science, statistics, and domain-specific knowledge. Machine learning engineers work on creating systems that can learn and improve from experience, allowing them to make predictions or decisions without being explicitly programmed for each task. Key responsibilities of a machine learning engineer may include data collection and pre-processing, gathering relevant data and preparing it for analysis by cleaning, transforming, and organizing it. Model development, designing and building machine learning models using various algorithms and techniques based on the nature of the problem. Training and evaluation, training models with labeled data, fine-tuning parameters, and evaluating model performance using appropriate metrics. Feature engineering, identifying and selecting relevant features, input variables that will enhance the model's predictive capabilities. Deployment, integrating machine learning models into production systems, ensuring they work in real-world scenarios and deploying them for practical use. Optimization, improving the efficiency and effectiveness of machine learning models by fine-tuning algorithms, adjusting parameters, and exploring new techniques. Continuous learning, staying updated with the latest advancements in machine learning and related fields, and integrating new techniques into existing projects when applicable. Collaboration, working closely with cross-functional teams, including data scientists, software engineers, and domain experts to understand business requirements and develop solutions. Machine learning engineers play a crucial role in the development and implementation of artificial intelligence applications, contributing to advancements in various industries such as healthcare, finance, e-commerce, and more. Becoming a machine learning engineer involves acquiring a combination of theoretical knowledge, practical skills, and hands-on experience. Here is a comprehensive list of steps you can follow to go from a beginner to a proficient machine learning engineer. Understand the basics of programming. Understanding programming. Programming is the methodical process of providing precise instructions to a computer. It's comparable to guiding a friend through the step-by-step process of making a sandwich. In the digital context, you establish communication with a computer through a programming language. Imagine you have a friend who has never made a sandwich before and you need to guide them through each step. Similarly, a computer is incredibly powerful but lacks intuition. It needs explicit instructions on what to do. This is where programming comes in. You break down a task into a logical steps that the computer can follow. Example, in everyday language, if you tell your friend, spread peanut butter on bread, it's a straightforward instruction. In programming, you use a programming language to give similarly clear and unambiguous commands to the computer. For instance, you might write a line of code that says, spread peanut butter on bread. This line of code serves as a direct instructions to the computer. It says, execute the function, spread peanut butter on bread. It's akin to your friend executing the action of spreading peanut butter on a slice of bread based on your verbal instruction. Programming languages act as intermediaries, translating human readable instructions into machine executable actions. Just as a friend follows your sandwich making guidance, a computer follows your programmed instructions to perform tasks and solve problems. The precision and clarity of your instructions in the programming language are crucial for the computer to carry out tasks accurately. Programming languages. Programming languages are the tools we use to communicate with computers. They provide a structured way to give instructions and are instrumental in developing software, applications, and various digital solutions. Each programming language has its own set of rules, syntax, and serves specific purposes. Types of programming languages. Python purpose. Python is a versatile language used for web development, data analysis, machine learning, artificial intelligence, and more. Example use case. If you are aimed to perform data analysis or venture into machine learning, Python's simplicity and extensive libraries make it a popular choice. JavaScript purpose. JavaScript is primarily used for web development, enabling dynamic and interactive features on websites. Example use case. If your goal is to create dynamic and responsive website with features like interactive forms or real-time updates, JavaScript is a go-to language. Java purpose. Java is known for its platform independence, making it suitable for building large-scale applications, mobile apps, Android, and enterprise-level systems. Example use case. If you are developing a robust and scalable enterprise application or an Android mobile app, Java might be the language of choice. C++ purpose. C++ is widely used for system software development, game development, and performance critical applications. Example use case. When you need to build high performance applications such as games or system level software, C++ provides the necessary control over hardware resources. Choosing a programming language. Your choice of programming language depends on the specific goals of your project. Consider the following factors. Project requirements. Different languages excel in different domains. Determine the nature of your project and choose a language that aligns with its requirements. Learning curve. Some languages are more beginner friendly, while others might have a steeper learning curve. Consider your level of experience and comfort with the language's syntax. Community and support. A strong community and good documentation are valuable resources. Languages with active communities often have extensive libraries and resources for problem solving. Scalability. If you are building a project that might grow in scale, consider the scalability of the language. Some languages are better suited for large-scale applications. In summary, the choice of programming language is a crucial decision that influences the success of your project. Understanding the strengths and use cases of different languages empowers you to make informed decisions based on the requirements of your programming endeavors. Basic programming concepts. Before embarking on coding in a specific programming language, it's essential to grasp fundamental programming concepts. These concepts serve as the building blocks for creating any software or application. Here are key concepts to understand. Variables. Explanation. Variables are like containers that hold information. They act as symbolic names for values or data. You can think of them as storage units that store different pieces of information. Example, in a recipe analogy, variables are like ingredients. For instance, ingredient 1 might represent the amount of flour and ingredient 2 could represent the amount of sugar. Data types. Explanation. Data types define the type of values that variables can hold. Common data types include integers, floating point numbers, strings, and Boolean values. Example, in the recipe analogy, data types are the categories of ingredients Liquids, solids, and powders represent different data types. For instance, the amount of water, liquid, is different from the amount of sugar, solid. Control structures, loops and conditionals. Explanation. Control structures dictate the flow of a program. Loops repeat a set of instructions while conditionals make decisions based on conditions. Example. In the recipe analogy, a loop is like repeating a step until a certain condition is met, such as stirring a mixture until it reaches a certain consistency. Conditionals are akin to deciding whether to add sugar based on tasting the batter. Functions. Explanation. Functions are blocks of reusable code that perform a specific task. They help in organizing code and making it more modular. Example. In the recipe analogy, functions are the steps in the recipe. For example, you might have a function called mix ingredients that combines various ingredients. Algorithms. Explanation. An algorithm is a step-by-step set of instructions to perform a specific task or solve a problem. It is the logical sequence of actions to achieve a desired outcome. Example. In the recipe analogy, the entire recipe is an algorithm. It's a series of well-defined steps, functions, that when followed in order lead to the desired result, a delicious dish. Understanding these basic programming concepts is crucial for writing clear, logical, and efficient code. It provides a foundation that makes it easier to transition between different programming languages and apply programming principles to diverse projects. Problem solving skills. Programming. Problem solving is at the core of programming. It's the ability to break down complex challenges into smaller, more manageable parts and devise effective solutions using code. Here is a detailed look at the crucial skill. Identifying the problem. Explanation. The first step is understanding the problem at hand. This involves analyzing the requirements, recognizing patterns, and defining the desired outcome. Example. Imagine you are tasked with creating a program to calculate expenses. Identifying the problem would involve understanding the steps needed, gathering input, expenses, performing calculations, and displaying results logically. Decomposing the problem. Explanation. Break the main problem into smaller, more manageable subproblems. This simplifies the overall task and makes it easier to address individual components. Example. Decomposing the expense calculation problem involves dividing it into subproblems such as input collection, calculation of totals, and presenting the results. Algorithmic thinking. Explanation. Develop a step-by-step plan or algorithm to solve each subproblem. Think about the logical sequence of actions needed to achieve the desired outcome. Example. For the expense calculation, algorithmic thinking involves outlining steps like receiving input, performing mathematical operations, and formatting the results. Implementing solutions. Explanation. Translate your algorithm into actual code. This is where your programming language skills come into play. Example. Writing code to collect input, perform calculations, and display results in a way that makes sense to the user. Testing and debugging. Explanation. Test your code to ensure it works correctly. If issues arise, use debugging skills to identify and fix problems. Example. For the example calculation program, testing involves entering various inputs and verifying that the results match expectations. Debugging is necessary if unexpected outcomes occur. Iterative refinement. Explanation. Continuously refine and optimize your code. Consider feedback, address and shortcomings, and improve the efficiency of your solutions. Example. If user find the expense calculation program cumbersome, you might refine the user interface or streamline the calculation process based on feedback. Creativity in solutions. Explanation. Sometimes problems don't have straightforward solutions. Being creative in finding alternative approaches can lead to more efficient or elegant code. Example, if there are multiple ways to display results in the expense calculation program, creative thinking may help in choosing a visually appealing and user-friendly format. Problem-solving skills are honed through practice and experience. They are not only vital for writing code but also for designing efficient and effective solutions to a wide range of challenges in the programming world. Learning resources. Learning programming is an exciting journey, and a plethora of resources are available to help you master the skills. Here is a detailed explanation. Online platforms. Explanation. Utilize interactive online platforms that offer courses and hands-on coding exercises. These platforms provide a structured learning path and often include interactive coding environments. Example, platforms like Codecademy, Audacity, and Free Code Camp are akin to having a personal tutor. They guide you step by step, allowing you to practice coding in a supportive online environment. Interactive coding exercises. Explanation. Learning by doing is crucial in programming. Interactive coding exercises on platforms enable you to apply theoretical knowledge in a practical setting, reinforcing your understanding. Example, Codecademy, for instance, provides exercises where you write and execute code directly in your browser. This hands-on experience solidifies your comprehension of programming concepts. Online courses. Explanation. Enroll in online courses that cater to your skill level. From beginners to advanced, courses often include video lectures, quizzes, and assignments to enhance your learning experience. Example, websites like Coursera and edX offer courses from universities and institutions worldwide. These courses cover a range of programming languages and topics, allowing you to learn at your own pace. Books by reputable authors. Explanation. Books written by experienced authors provide in-depth knowledge and often offer a more comprehensive understanding of programming concepts. They can serve as valuable reference materials. Example, books such as Clean Code by Robert C. Martin or Introduction to Algorithms by Thomas H. Corman provide deep insights into coding practices and algorithmic principles, respectively. Community forums and blogs. Explanation. Engage with the programming community through forums like Stack Overflow and tech blogs. These platforms allow you to seek help, share experiences, and stay updated in industry trends. Example, participating in discussions on Stack Overflow not only helps you find solutions to specific coding problems but also exposes you to diverse perspectives and approaches in programming. Project-based learning. Explanation. Embark on project-based learning to apply your skills in real-world scenarios. Building projects allows you to integrate knowledge from various sources and gain practical experience. Example, platforms like GitHub provide repositories of open source projects. Contributing to such projects or initiating your own can enhance your problem solving and collaboration skills. Programming communities and meetups. Explanation. Join local or online programming communities and attend meetups. Networking with fellow learners and professionals provides valuable insights, mentorship, opportunities, and motivation. Example, meetup.com often hosts local coding meetups. Connecting with like-minded individuals can foster a supportive learning environment and open doors to collaborate projects. Official documentation. Explanation. Don't overlook official documentation for programming languages and frameworks. These resources provide authoritative information on syntax, features, and best practices. Example, the official documentation for Python or JavaScript is an invaluable resource for understanding the intricacies of these languages. Remember that everyone learns differently, so exploring a combination of these resources can be beneficial. The key is to maintain a consistent and dedicated approach to your learning journey. Building projects. Applying your knowledge through hands-on projects is a crucial step in the learning process. Here is an in-depth explanation. Practical application of knowledge. Explanation. Building projects allows you to apply theoretical knowledge in a practical setting. It's where you take concepts, learning from tutorials and courses, and integrate them into a real-world context. Example, if you have learned web development, creating a personal website involves using HTML, CSS, and JavaScript to build an actual application rather than just understanding the syntax. Skill integration. Explanation. Projects provide a platform to integrate multiple skills. Instead of focusing on individual concepts, you bring together various technologies and techniques to solve a problem or create a product. Example, in a web development project, you may combine front-end technologies, HTML, CSS, JavaScript, with back-end technologies, Node.js, Python, Ruby, to create a fully functional web application. Problem solving in real scenarios. Explanation. Projects often present real-world problems that require creative solutions. This challenges you to think critically, solve problems independently, and apply your programming skills to overcome hurdles. Example, analyzing a dataset for a data analysis project involves not only applying statistical methods but also interpreting the results in a meaningful way. Portfolio development. Explanation. Completed projects serve as a tangible portfolio of your skills. Whether you are showcasing your work to potential employers or collaborators, a portfolio demonstrates your practical abilities. Example, your personal website created as a web development project becomes a showcase of your design skills, coding proficiency, and creativity. Demonstrating expertise. Explanation. A well-executed project serves as evidence of your expertise in particular area. It can be a powerful tool during job interviews. Demonstrate your practical skills and problem-solving abilities. Example, if you are interested in machine learning, a project that involves training a model to predict outcomes in a specific domain showcase your understanding and application of machine learning concepts. Learning through challenges. Explanation. Projects often come with challenges and uncertainties. Overcoming these challenges enhances your problem-solving skills. Resilience and adaptability essential qualities for a programmer. Example, when building a mobile app, you might face compatibility issues or encounter unexpected bugs. Solving these challenges contributes to your growth as a developer. Personal satisfaction and motivation. Explanation. Completing a project provides a sense of accomplishment and boosts motivation. It's a tangible result of your efforts, reinforcing your commitment to continuous learning. Example, finishing a game development project, for instance, not only demonstrates your programming skills but also provides the satisfaction of creating a playable game from scratch. Community engagement. Explanation. Sharing your projects with the programming community invites feedback and collaboration. Engaging with others in the community provides valuable insights, alternative perspectives, and opportunities for improvement. Example, posting your open source project on GitHub allows others to contribute, providing a collaborative platform for learning and sharing knowledge. In summary, building projects is an integral part of the learning journey in programming. It transforms theoretical knowledge into practical skills, creating a portfolio that not only showcases your abilities but also demonstrates your passion and commitment to the field. Collaboration and version control. Collaborating with other programmers and implementing version control systems are essential aspects of modern software development. Here is a detailed explanation. Team collaboration. Explanation. Many software projects involve collaboration among multiple developers. Version control facilitates seamless teamwork, enabling contributors to work on different parts of the project simultaneously. Example, collaborating on a project is similar to writing a book with a co-author. Each author can work on different chapters concurrently, and version control helps manage the changes made by each author. Version control systems, VCS. Explanation. Version control systems like Git, GIT, track changes made to code over time. They allow developers to collaborate, roll back to previous versions, and merge changes efficiently. Example, think of version control as having a detailed history of your book. If you decide to rewrite a paragraph, you can easily refer to previous versions, ensuring a smooth and organized writing process. Git and GitHub. Explanation. Git is a widely used distributed version control system. GitHub, a web-based platform built around Git, provides a centralized space for hosting and collaborating on Git repositories. Example, using Git and GitHub is akin to having a shared online workspace for your book. Co-authors can make changes, propose edits, and track the evolution of the manuscript in a centralized location. Explanation. In collaborative projects, conflicts may arise when multiple contributors make changes to the same file simultaneously. Version control systems provide tools to resolve conflicts efficiently. Example, imagine two co-authors editing the same paragraph in your book. Conflict resolution tools in version control help reconcile the changes made by each author to maintain a coherent narrative. Rollbacks and reverts. Explanation. Version control allows you to roll back to a previous state of the code if needed. This is useful in case an update introduces issues or unintended consequences. Example, if a chapter of your book takes an unexpected turn, version control enables you to revert to a previous version, preserving the original content. Documentation and collaboration platforms. Explanation. Collaboration platforms, often integrated with version control systems, provide space for documentation, issue tracking, and communicating among team members. Example, documentation in your book project could include notes on character backgrounds, plot outlines, and feedback. Collaboration platforms ensure that this information is accessible to all co-authors. Continuous integration, CI, and continuous deployment, CD. Explanation. CI/CD practices automate the testing and deployment of code changes. This ensures that new features are integrated smoothly into the existing code base. Example, in your book writing analogy, CI/CD would be equivalent to having an editor review each chapter before it becomes part of the final manuscript, ensuring consistency and quality. In summary, learning to collaborate using version control systems is crucial for the success of software projects. It provides a structured and efficient way for multiple developers to work together, manage changes, and maintain the integrity of the code base. Just as co-authors need a systematic approach to writing a book, developers benefit from version control to streamline their collaborative efforts. Learning a programming language, Python. Explanation. Picture programming languages as diverse languages for conversing with computers. Python stands out for its readability and simplicity in coding. Selecting a programming language is akin to choosing a communication style. Python resembles articulating ideas in straightforward and clear sentences. Example, consider learning Python as picking up a language for storytelling. Python's syntax is like crafting a narrative with clear sentences, making it accessible for both beginners and experienced developers. Understanding Python's readability. Explanation. Python's emphasis on readability means its code resembles plain English, making it easier to comprehend and write. This readability is a distinctive feature that contributes to Python's popularity. Example, if you were to explain a complex concept to a friend, you would use simple and clear language. Python, with its readable syntax, allows you to convey instructions to the computer in a similar, straightforward manner. Choosing Python for simplicity. Explanation. Python's simplicity lies in its minimalistic and clean syntax. It avoids unnecessary complexity, which is particularly beneficial for beginners entering the world of programming. Example. Imagine explaining a task to someone using the fewest words possible. Python's simplicity allows you to express complex operations concisely, making coding feel like a conversation rather than a technical jargon. Treating Python like a language. Explanation. Approach learning Python as acquiring a new language. Focus on understanding its vocabulary, syntax, grammar, structure, and how to articulate ideas effectively. Example. Learning Python is akin to studying a language. You start with basic phrases, commands, gradually construct sentences, functions, and eventually develop fluency in expressing intricate thoughts, coding solutions. Practical use of Python. Explanation. Python's versatility extends to various applications from web development to data science. Understand the practical use of Python to appreciate its relevance different domains. Example, just as you might choose a language for specific purposes, that is English for business, French for romance, Python becomes your go-to tool for specific tasks, whether it's creating websites or analyzing data. Building Python conversations. Code. Explanation. In Python, you are essentially constructing conversations with the computer. Every line of code is a sentence, and the overall script is a narrative that guides the computer through a series of actions. Example. Consider writing a Python script like composing a dialogue. Each line contributes to the flow of the conversation, with the computer responding to your instructions as if it understands your language. Why Python? Explanation. Think of Python as a helpful companion in the world of programming. Its widespread use in machine learning, where computers learn and make decisions, highlights its effectiveness as a tool for teaching computers complex tasks. Python simplifies the process, acting as a friendly guide in conveying our instructions to the computer. Example. Consider Python as a reliable assistant, much like a tutor guiding a student. In the realm of machine learning, Python plays the role of a patient instructor, making it easier for us to impart knowledge to the computer and train it to perform specific tasks. Python's friendliness in programming. Explanation. Python's syntax and structure are designed to be user-friendly, promoting a comfortable and readable coding experience. This friendliness is particularly advantageous for both engineers and experienced developers. Example. Think of Python as a congenial guide in a foreign land. Its syntax is like clear directions, ensuring that anyone, regardless of their programming expertise, can navigate and communicate effectively with the computer. Python's dominance in machine learning. Explanation. Python has become the language of choice in the field of machine learning. Its extensive libraries and frameworks, such as TensorFlow and PyTorch, provide powerful tools for developing and implementing machine learning algorithms. Example. In the world of machine learning, Python is like the lingua franca. Just as English is widely spoken across various cultures, Python is embraced in the machine learning community for its adaptability and extensive support. Teaching computers with Python. Explanation. The essence of machine learning is teaching computers to learn and make decisions. Python's simplicity and readability make it an ideal language for expressing these instructions and training computers effectively. Example. Imagine Python as a patient teacher in a classroom. You provide instructions in a clear and understandable manner, and Python ensures that the computer comprehends and learns from these instructions, much like a student absorbing knowledge. Python's facilitation of complex tasks. Explanation. Python excels in simplifying complex tasks in machine learning where intricate algorithms and computations are involved. Python's clarity and conciseness make it easier for programmers to handle sophisticated challenges. Example. Think of Python as a problem-solving companion. When faced with the complex task, Python is like a reliable partner, helping you break down the problem into manageable steps and providing a clear path to solution. Python's role in expressing intent. Explanation. Python allows programmers to express their intent clearly and concisely. This is particularly crucial in machine learning where precision in conveying instructions to the computer is paramount. Example. Consider Python as a language for negotiations. In machine learning, you negotiate with the computer by expressing your intent through Python code, ensuring that the computer understands and executes your instructions accurately. Daily routine example. Explanation. Think of your daily routine as a set of instructions you give the computer. Imagine creating a list of your favorite books in Python. You instruct the computer to make a list and add each book to it. This Python code snippet illustrates this process. Example. Consider your daily routine as a script for the computer. If you were creating a list of your favorite books, you would start by telling the computer to make an empty list and then add each book to it, just like creating a to-do list for your day. How Python helps in machine learning. Explanation. Machine learning involves computers learning patterns and making decisions without explicit programming. Python serves as a powerful tool for writing code that instructs the computer in recognizing and understanding these patterns. It's like teaching the computer by providing it with examples, such as showing it numerous pictures of cats to enable it to recognize a cat in a new picture. Example. Think of Python as the language of instruction in a classroom where the computer is the student. In machine learning, you don't provide explicit rules. Instead, you guide the computer by exposing it to examples, showing the computer many pictures of cats through Python code is akin to conducting a visual lesson, allowing the computer to generalize and recognize cats in unseen images. Python's role in writing machine learning code. Explanation. Python's versatility and simplicity make it an ideal language for writing code in machine learning. Libraries and frameworks like TensorFlow, PyTorch, and scikit-learn provide tools for implementing machine learning algorithms effectively. Example. Imagine Python as a language for crafting lessons. In machine learning, Python code is like a lesson plan, outlining the steps for the computer to learn and make decisions based on data patterns. Teaching computers patterns with Python. Explanation. Python allows programmers to create algorithms that expose computers to patterns in data. For example, in image recognition, Python code can be written to analyze thousands of images and identify common features of a particular object. Example. Consider Python as a teaching assistant in machine learning. Python helps you design lessons for the computer, showing it patterns in data. If you want the computer to recognize cats, you would use Python to guide it through a dataset of cat images, teaching it the distinguishing features. Python for recognition tasks. Explanation. Python excels in handling recognition tasks such as image or speech recognition. Machine learning models built with Python can be trained to recognize patterns in diverse data, enabling the computer to make accurate decisions. Example. Think of Python as a guide in a museum. If you want the computer to recognize artwork patterns, Python helps you design a learning process, for example, showing it various paintings data so it can identify the style or artist. Generalization with Python in machine learning. Explanation. Python enables the creation of machine learning models that can generalize from examples. This means the computer can apply its learning to new unseen data, making predictions or decisions based on the patterns it has learned. Example. Consider Python as a language for storytelling. In machine learning, Python helps you tell a story to the computer using data. The computer, like a keen listener, learns the plot patterns and can predict how a new story, unseen data, might unfold. Python's contribution to decision making. Explanation. Python empowers the development of machine learning models that make decisions autonomously. The computer trained with Python code can apply its learning to new situations, making informed decisions based on the patterns it has discovered. Example. Think of Python as a mentor guiding decision making. In machine learning, Python helps you mentor the computer, teaching it decision making skills by presenting examples and allowing it to learn and adapt to new scenarios. Why start with basics? Explanation. Starting with the basics in programming is akin to learning the alphabet before writing a story. Just as understanding the fundamentals of language enables coherent communication, grasping the basics of programming helps in giving clear and structured instructions to the computer. Once the foundation is solid, it becomes easier to tackle more complex tasks, such as machine learning. Example. Consider programming as a language for communication with computers. Learning the basics is like mastering the alphabet and grammar, the essential components that allow you to express your thoughts clearly. Once you are familiar with these fundamentals, you can start building more intricate programs, just as you can compose complex narratives once you know the alphabet. Clear instructions to the computer. Explanation. Learning the basics of programming involves understanding how to give precise and unambiguous instructions to the computer. This clarity is essential for the computer to execute tasks accurately. Example. Think of programming as writing a set of instructions for a recipe. Starting with the basics is like ensuring that your recipe instructions are clear and specific so anyone following them can recreate the dish successfully. Building a strong foundation. Explanation. The basics from the foundation of programming knowledge. Concepts such as variables, data types, and control structures are like the building blocks upon which more complex programs are constructed. Example. Imagine constructing a house. You start with a solid foundation before adding walls, rooms, and intricate details. Similarly, learning the basics in programming establishes a strong foundation for more advanced concepts and applications. Progressing to complex tasks. Explanation. Mastering the basic is a stepping stone to handling more complex programming tasks. Once you are comfortable with the fundamentals, you can confidently explore advanced topics like machine learning, web development, or data analysis. Example. Consider learning to play a musical instrument. Mastering the basics like scales and simple melodies is essential before attempting complex compositions. Likewise, understanding programming basics prepare you for more sophisticated coding challenges. Problem solving skills. Explanation. Starting with the basics cultivates problem solving skills. Learning how to approach and solve simple problems sets the stage for tackling more intricate and real-world challenges in programming. Example. Think of programming as solving puzzles. Starting with simple puzzles helps you develop strategies and techniques that you can later apply to more complex puzzles. Similarly, mastering basic programming concepts hones your problem-solving skills. Preparation for advanced concepts. Explanation. Basic programming concepts serve as prerequisites for understanding and applying advanced topics. Concepts like loops, functions, and conditionals provide the groundwork for more sophisticated programming structures. Example: consider learning a sport. Mastering fundamental skills like dribbling and passing prepares you for advanced techniques. Similarly, understanding basic programming concepts prepare you for the intricacies of machine learning, data science, and other advanced applications. Summary: programming as a language. Learning programming is compatible to acquiring a new language. Python, being a friendly and widely used language, facilitates effective communication with computers. Python's friendliness. Python's chosen for its readability and simplicity, making it akin to speaking in a clear and straightforward manner. It acts as a friendly and accessible language for both beginners and experienced developers. Communication with computers. Mastering Python allows you to give precise instructions to computers. This communication is crucial for making computers perform diverse and remarkable tasks such as recognizing images of cats or providing book recommendations. Regular practices. Similar to practicing a new language, consistent programming practice is essential for improvement. Making programming a regular part of your routine, like any other skill, enhances proficiency and confidence in using the language effectively. Python's versatility. Python's versatility extends beyond basic communication with computers. It becomes a powerful tool for more advanced applications such as machine learning, where you can teach computers to recognize patterns and make informed decisions. Integration into routine. Integrating programming into your routine is key to mastering it. Just as you would practice a musical instrument or a sport regularly, regular engagement with programming helps you become more adept at utilizing this valuable skill. In essence, learning programming, especially through the friendly language of Python, opens doors to creative possibilities in interacting with computers and solving real-world challenges. Regular practice and integration into your routine are the keys to unlocking the full potential of this skill. Building a strong foundation in mathematics. What is mathematics? Explanation. Mathematics is akin to the language of numbers and shapes. It serves as a universal tool for understanding, describing, and solving problems in the world. Much like words in a language help us communicate, mathematics provides a structured and precise method for expressing relationships, patterns, and quantities. Example: consider mathematics as the language of problem solving. When faced with a real world challenge, mathematics allows us to articulate and analyze the problem in a systematic way, much like using words to convey thoughts and ideas. Language of numbers. Explanation. In its numeric form, mathematics allows us to quantify, measure, and manipulate numbers. It provides a framework for expressing numerical relationships and performing calculations. Example: think of mathematics as the script for counting and measuring. Numbers, like words in a sentence, convey information and enable us to perform various operations such as addition, subtraction, multiplication, and division. Language of shapes. Explanation. Mathematics extends to the world of shapes and special relationships. Geometry, a branch of mathematics, helps us understand and describe the properties of objects in space. Example: imagine mathematics as the guidebook for understanding shapes. Geometry, like a language, allows us to describe the dimensions, angles, and relationships between shapes, just as words helps us describe the characteristics of objects. Problem solving tool. Explanation. Mathematics is a powerful tool for solving problems. It provides a systematic approach to breaking down complex issues, formulating solutions, and analyzing patterns. Example: consider mathematics as a toolkit for problem solving. When faced with a challenge, mathematics enables us to deconstruct the problem, identify relevant variables, and apply logical processes to arrive at a solution. Universal language explanation. Mathematics is considered a universal language because its principles and concepts are consistent and applicable across different cultures and contexts. Example: think of mathematics as a language spoken worldwide, whether you are in Asia, Europe, or the Americas. The principles of mathematics remain the same, much like the consistency of language across diverse regions. Precision and clarity explanation. Mathematics emphasizes precision and clarity in expressing ideas through mathematical notation and symbols. Complex concepts can be communicated with accuracy. Example: consider mathematics as a language that eliminates ambiguity. Mathematical symbols and notation provide a clear and concise way to express relationships and formulas, similar to how specific words convey precise meanings in language. In essence, mathematics serves as a structured and universal language that empowers us to explore, analyze, and comprehend the intricacies of the world around us. Linear algebra, understanding relationships. Explanation. Linear algebra is comparable to playing with building blocks. In this context, each block represents a different element or variable in problems. The power of linear algebra lies in its ability to help you understand and analyze how these elements, blocks, relate to each other. Similar to figuring out relationships between different types of building blocks. Example: imagine you have building blocks representing apples A and oranges O. Linear algebra acts as a toolkit for understanding the relationships between these blocks, much like figuring out how many apples and oranges you have in a collection. Everyday example, linear algebra. Explanation. Consider a scenario where you have 2 apples A and 3 oranges O. In linear algebra, you can represent this situation with a simple equation. 2 plus 3, 2A plus 3O. Example: think of this equation as a mathematical representation of your collection of apples and oranges. The coefficients 2 and 3 indicates the quantities of each type of fruit, and the variables A and O represent apples and oranges, respectively. Linear algebra allows you to express and manipulate these relationships in a concise and systematic way. In essence, linear algebra provides a structured approach to representing and understanding relationships between different elements, making it a powerful tool for solving problems in various fields, including mathematics, computer science, and physics. Calculus, understanding change. Explanation. Calculus is akin to the study of how things change. In this context, it provides tools and methods to understand the rate at which quantities change over time. It's like examining the dynamics of a situation, such as tracking the speed of a car and figuring out how that speed is changing at each moment, whether the car is accelerating or decelerating. Example: imagine you are observing the speed of a car over time. Calculus enables you to delve into the nuances of this change, allowing you to grasp not just the average speed, but how the speed varies at each instant, providing insights into whether the car is speeding up or slowing down. Everyday example, calculus. Explanation. Consider a scenario where you are driving a car and your speed is changing. Calculus comes into play when you want to understand how quickly your speed is changing at any given moment. Example: think of driving your car as dynamic experience. If your speed is not constant but changing, calculus helps you precisely determine the rate of change of your speed. It answers questions like how rapidly you are accelerating or decelerating, providing valuable insights into the dynamic nature of your motion. In summary, calculus is a mathematical framework that allows us to explore and quantify changes in various phenomena, whether it's tracking the speed of a car, analyzing the growth of populations, or understanding the behavior of natural processes. Calculus serves as a powerful tool for studying and interpreting change in the world around us. Probability, statistics, dealing with uncertainty. Explanation. Probability and statistics are comparable to playing with chances and data. Probability comes into play when expressing the likelihood of events, while statistics is the tool for analyzing data to make informed predictions. It's like navigating uncertainties, such as predicting whether it will rain tomorrow. Example. Imagine you are predicting the chance of rain. Probability allows you to express the likelihood, and statistics helps you analyze historical weather data to make informed predictions about future events. Everyday example, probability, statistics. Explanation. Consider a scenario where there is a 70% chance of rain tomorrow. Probability expresses this likelihood and statistics enters the scene when you analyze past weather data to make predictions about the future. Example. Think of this as a practical application of probability and statistics. The 70% chance of rain is a probability, indicating the likelihood of a specific event occurring. Meanwhile, statistics, drawing insights from historical weather data, allows you to make an informed prediction about the likelihood of rain based on past patterns and trends. In summary, probability and statistics provide a framework for dealing with uncertainty and making informed decisions in the face of incomplete information, whether it's predicting weather, analyzing survey results, or making financial forecasts. These mathematical tools play a crucial role in navigating the uncertainties of the real world. Importance of mathematics in machine learning. Explanation. Similar to how a strong foundation in language aids in expressing complex ideas, a robust understanding of mathematics serves as the backbone for comprehending and creating intricate algorithms in machine learning. Examples. Think of mathematics as the language of machine learning. Just as a linguist needs a deep understanding of language structures to convey nuanced thoughts, a machine learning practitioner requires a solid grasp of mathematical concepts to build, analyze, and optimize complex algorithms. Algorithmic understanding. Explanation. Mathematics provides the tools for understanding and formulating algorithms. Concepts from linear algebra, calculus, and probability theory are fundamental for designing algorithms that can learn from data and make predictions. Data representation and transformation. Explanation. Mathematics plays a crucial role in representing and transforming data. Linear algebra is particularly essential for working with data in the form of vectors and matrices, allowing efficient computation and manipulation. Example. In machine learning, data often comes in the form of numerical features. Linear algebra operations such as matrix multiplication are employed to transform and process this data, making it suitable for training models. Optimization and training models. Explanation. Optimizing machine learning models involves minimizing or maximizing mathematical functions. Calculus, especially optimization techniques, is fundamental for fine-tuning models and enhancing their performance during the training process. Example. Picture training a machine learning model as adjusting the weights in a mathematical equation. Calculus helps find the optimal value for these weights, ensuring that the model makes accurate predictions on new unseen data. Probability and uncertainty handling. Explanation. Probability theory is essential for dealing with uncertainty in machine learning. It provides a framework for making decisions in situations where outcomes are uncertain. a common scenario in real-world applications. Example, in tasks like classification or recommendation systems, understanding and managing uncertainties are crucial. Probability theory allows machine learning models to express confidence levels in their predictions. Generalization and model evaluation. Explanation. Mathematics aids in understanding the generalization of machine learning models, how well they perform on new, unseen data. Statistical concepts are employed to evaluate and validate the effectiveness of models. Example, think of model generalization as the ability to apply learned patterns to new situations. Statistical methods such as cross-validation help assess how well a model will perform on data it has not seen during training. In essence, a strong foundation in mathematics is the key to unlocking the full potential of machine learning. It empowers practitioners to design robust algorithms, efficiently process and present data optimize models, handle uncertainty, and evaluate the performance of machine learning systems. Daily routine example explanation. Devoting a portion of your daily routine to practicing math is akin to engaging in a regular exercise routine. Just as consistent physical exercise keeps your muscles strong, daily math practice helps maintain and strengthen your mathematical skills. It allows you to tackle various problems from calculating expenses to making predictions based on available data. Example, consider your daily math practice as a workout for your mind, much like performing exercise to maintain physical health. Solving math problems regularly is a mental exercise that keeps your mathematical abilities in top shape. Regular exercise for math muscles. Explanation. Daily math practice serves as regular exercise for your math muscles. It involves solving problems, working with formulas, and applying mathematical concepts which collectively keep you mental health skills sharp. Example, think of each math problem you solve as a repetition in your mental exercise routine, whether it's calculating expenses, solving equations, or analyzing data. Each task contributes to the overall strength and agility of your math skills. Strengthening problem solving abilities. Explanation. Practicing math daily enhances your problem solving abilities. It allows you to approach problems with confidence, apply appropriate mathematical techniques, and find efficient solutions. Example, consider math problems as puzzles to be solved. Daily practice hones your problem solving skills, helping you develop strategies to tackle different types of problems, whether they involve budgeting, data analysis, or predictions. Practical application in daily tasks. Explanation. Daily math practice extends to practical applications in your daily tasks, whether you are calculating expenses, managing budgets, or making predictions based on available data. Math becomes a useful tool in your routine. Example, imagine managing your daily expenses as a math problem. Calculating your budget, expenses, and savings involves applying mathematical concepts to make informed decisions about your finances. Adaptability in various scenarios. Explanation. Regular math practice enhances your adaptability in various scenarios. It equips you with the skills to analyze and solve problems across different domains, from personal finance to data-driven decision making. Example, think of your math skills as a versatile toolkit. Daily practice ensures that you are ready to apply mathematical principles in diverse situations, adapting your problem-solving approach to different challenges. Continuous learning and improvement. Explanation. Daily math practice promotes continuous learning and improvement. It allows you to explore new concepts, reinforce existing knowledge, and gradually advance your mathematical proficiency. Example, consider your math practice routine as a continuous learning journey. Each day brings an opportunity to explore new mathematical challenges, reinforcing what you know and gradually expanding your mathematical toolkit. In summary, incorporating daily math practice into your routine is a proactive way to keep your mathematical skills sharp, foster problem solving abilities, and apply math to real world scenarios. It's a form of mental exercise that contributes to your overall mathematical fitness. Mathematics as a toolkit for understanding and solving problems. Explanation: mathematics serves as a versatile toolkit that equips individual with the tools necessary to understand, express, and solve a wide range of problems. Its various branches provide methods and frameworks for tackling different types of challenges. Linear algebra, understanding relationships. Explanation: linear algebra focuses on the study of relationship between variables, often represented as vector and matrices. It provides a powerful language for expressing and manipulating these relationships, making it a foundational tool in various mathematical and computational fields. Example: imagine linear algebra as a set of tools for building and understanding relationships between different quantities, whether it's analyzing data, solving systems of equations, or transforming geometric shapes. Linear algebra provides the means to express and comprehend these relationships. Calculus, dealing with change. Explanation: calculus is the branch of mathematics concerned with understanding change and motion. It provides techniques for studying rates of change, accumulation, and the behavior of functions, making it essential for modeling dynamic processes. Example: think of calculus as a set of tools for capturing change. Whether you are predicting the trajectory of a projectile, optimizing a system, or understanding the growth of a population, calculus provides the methods to analyze and quantify these changes. Probability, statistics, handling uncertainty. Explanation: probability and statistics are essential tools for dealing with uncertainty in data and predictions. Probability theory helps express the likelihood of events, while statistics provides methods for analyzing and interpreting data, making informed decisions in uncertain situations. Example: consider probability and statistics as tools for navigating uncertainties, whether you are predicting outcomes, analyzing survey results, or making decisions based on incomplete information. Probability and statistics offer a framework for handling uncertainty. Building a strong foundation for machine learning. Explanation: building a strong foundation in linear algebra, calculus, probability, and statistics is analogous to assembling a powerful set of tools for machine learning. These mathematical concepts form the basis for understanding, creating, and optimizing machine learning algorithms. Example: think of a strong foundation in mathematics as the cornerstone of machine learning expertise. It empowers practitioners to navigate complex algorithms, represent and transform data effectively, optimize models, and make informed decisions in uncertain situations. In summary, mathematics is indeed a toolkit, and a solid understanding of its various branches is instrumental in addressing a myriad of challenges, especially in the field of machine learning. The combination of linear algebra, calculus, and probability statistics form a powerful set of tools that empowers individuals to tackle problems with precision and depth. Studying machine learning fundamentals. What is machine learning? Explanation: machine learning is akin to the process of teaching computers to learn from data and make decisions without being explicitly programmed. In other words, it's a paradigm where computers can automatically learn and improve their performance over time based on experiences or examples, similar to how a person might learn from practice or exposure to various situations. Example: think of machine learning as the art of training a robot. Instead of providing explicit instructions for every possible scenario, You show the robot examples of the task you want it to perform. The robot learns from these examples and generalizes its knowledge to handle similar situations it has not explicitly encountered. Learning from data. Explanation. Machine learning emphasizes the learning process from data. Rather than relying on explicit programming, algorithms are designed to analyze and learn patterns from data, enabling computers to make informed decisions or predictions. Example. Consider feeding a machine learning algorithm a dataset of images and labels. The algorithm learns to recognize patterns in the images and can later classify new unseen images based on the learned patterns. Decision making without explicit programming. Explanation. In machine learning, the goal is to enable computers to make decisions without being explicitly programmed for each decision. The algorithms learn to generalize from examples, allowing them to apply their knowledge to new unseen situations. Example. Imagine a machine learning model trained on customer purchase data. Without explicit programming for each customer, the model can predict preferences and make personalized recommendations based on learned patterns. Training process. Explanation. The training process in machine learning is analogous to teaching or training. During this phase, the algorithm learns from examples, refines its understanding, and adjusts its parameters to improve performance. Example. Picture training a machine learning model like teaching a dog new tricks. You provide examples, training data, and adjust your teaching approach until the dog model learns to perform the desired tasks accurately. Generalization to new situations. Explanation. A key aspect of machine learning is the ability to generalize knowledge to new, unseen situations. The learned patterns should apply beyond the training data, allowing the algorithm to make accurate predictions in real-world scenarios. Example. If a machine learning model is trained to recognize different breeds of dogs, the goal is for it to generalize its knowledge and accurately identify new breeds it has not seen during training. Continuous improvement. Explanation. Machine learning models can continuously improve their performance as they encounter more data and experiences. This adaptability allows them to refine their decision-making abilities over time. Example. Think of a machine learning model as a student. The more examples, training data it sees, the more it learns and its performance improves over time, adapting to a changing environment. In summary, machine learning is a paradigm that enables computers to learn and make decisions from data, mimicking the way humans learn from experiences. It's a powerful approach that finds applications in diverse fields, from image recognition to natural language processing and beyond. Supervised learning. Learning with a teacher. Explanation. Supervised learning is akin to the process of learning with guidance, much like having a teacher to guide you through new concepts. In this context, the teacher provides labeled examples such as images of cats and dogs along with corresponding answers indicating which is which. The computer learns by comparing its predictions to the labeled examples provided by the teacher. Example. Imagine a teacher showing you pictures of cats and dogs and clearly stating which is which. The goal is for you to learn and generalize from these examples. So when presented with a new picture, you can correctly identify whether it's a cat or a dog. Similarly, in supervised learning, the computer learns by making predictions and adjusting its understanding based on the labeled training data. Guided learning process. Explanation. Supervised learning involves a guided learning process where the algorithm is provided with labeled examples during training. The labels serve as the ground truth, guiding the algorithm in refining its prediction. Example, think of the teacher as providing guidance during a lesson. The labeled examples act as a reference point for the algorithm, allowing it to learn and adjust its predictions with the aim of aligning them with the correct answers. Labeled training data explanation. In supervised learning, the training data set consists of labeled examples where each example is paired with its correct answer. This labeled data forms the basic for the algorithm to learn patterns and relationships. Example, consider the labeled images of cats and dogs as the training data. Each image is paired with a label indicating whether it's a cat or a dog. The computer uses the labeled dataset to learn and generalize its understanding. Predictions and feedback explanation. The algorithm makes predictions based on the input data, and these predictions are compared to the correct answers provided by the teacher. Any disparities between predictions and actual answers serve as feedback to adjust the algorithm. Example, imagine making predictions about new pictures of animals. If your teacher corrects any mistakes, you learn from those corrections. Similarly, in supervised learning, the algorithm refines its predictions based on feedback from the labeled examples. Goal of generalization explanation. The ultimate goal in supervised learning is for the algorithm to generalize its understanding beyond the training data. It should be able to correctly predict outcomes for new unseen examples that were not part of the training set. Example, think of the teacher's guidance helping you generalize to new situations. In supervised learning, the algorithm aims to generalize its learned patterns, ensuring accurate predictions for data it has not encountered during training. Common applications explanation. Supervised learning finds application in various fields from image and speech recognition to natural language processing. It is particularly effective when there is a clear relationship between input data and desired output, making it suitable for tasks with labeled examples. Example, consider a speech recognition system with labeled examples of spoken words and corresponding text. Supervised learning enables the algorithm to learn the mapping between audio signals and words, allowing it to transcribe new spoken words accurately. In summary, supervised learning is a guided learning process where the algorithm learns from labeled examples provided by a teacher. The labeled data serve as a foundation for the algorithm to make predictions and generalize its understanding to new unseen data. Everyday example, supervised learning. If you show a computer lots of pictures of cats labeled as cat and dogs labeled as dog, it learns to distinguish between them. So when you show it a new picture, it can tell you if it's a cat or a dog. Unsupervised learning, learning on its own. Explanation, unsupervised learning is comparable to the process of exploration without a teacher. In this scenario, the computer is presented with data such as a collection of pictures without explicit labels or guidance. The computer then endeavors to uncover inherent patterns or structures in the data on its own. Example, imagine exploring a collection of photos without any prior information or labels. In unsupervised learning, the computer autonomously seeks patterns and similarities in the data, grouping similar photos together based on inherent features. Everyday example, unsupervised learning. Explanation, consider a scenario where you have a collection of photos and the computer organizes them into groups based on similarities. This process mirrors unsupervised learning where the algorithm autonomously identifies patterns or clusters within the data. Example, picture having a mix of beach and mountain photos without explicit labels. In unsupervised learning, the computer autonomously discerns patterns and might organize the photos into distinct groups. such as putting all beach photos in one group and mountain photos in another, based on inherent similarities. Exploration and discovery, explanation. Unsupervised learning involves the algorithm exploring the data and discovering patterns without predefined labels. The process is driven by the algorithm's ability to discern inherent structures within the data. Example: think of exploring a new environment without a guide. Similarly, in unsupervised learning, the algorithm explores the data landscape without predefined labels, seeking patterns and structures on its own. Clustering and grouping, explanation. A key aspect of unsupervised learning is clustering or grouping similar data points together based on shared characteristics. The algorithm autonomously identifies these clusters without external guidance. Example: consider the computer organizing photos into groups. In unsupervised learning, the algorithm might cluster photos with similar visual features, grouping beach photos together and mountain photos into a separate cluster. Pattern recognition, explanation. Unsupervised learning involves the algorithm recognizing patterns within the data, even when those patterns are not explicitly defined. It seeks to understand the inherent structures present in the dataset. Example: imagine recognizing recurring themes in a collection of photos without knowing the specific labels. Similarly, in unsupervised learning, the algorithm recognizes patterns or commonalities within the data without relying on predefined labels. Anomaly detection, explanation. Unsupervised learning is also capable of detecting anomalies or outliers within the data instances that deviate from the expected patterns. This is achieved by identifying data points that differ significantly from the majority. Example: consider identifying an unexpected photo in a collection. Unsupervised learning can similarly detect anomalies such as a photo that deviates significantly from the overall visual characteristics of the dataset. Application in real-world scenarios, explanation. Unsupervised learning finds applications in real-world scenarios where the data lacks explicit labels or predefined categories. It is particularly useful for tasks such as clustering, dimensionality reduction, and uncovering hidden structures in data. Example: think of sorting and organizing a diverse set of documents without predefined categories. Unsupervised learning algorithms can be applied to cluster similar documents together based on their content or structure. In summary, unsupervised learning represents a form of exploration where the algorithm autonomously discovers patterns and structures within data without explicit guidance. It is a powerful approach for tasks where labeled examples are unavailable, enabling the algorithm to unveil inherent relationships and groups in the data. Reinforcement learning, learning from rewards, explanation. Reinforcement learning is comparable to the process of teaching through a system of rewards and penalties. In this scenario, the computer, like a virtual pet or a trainable agent, learns by receiving rewards for good actions and penalties for bad ones. The goal is for the computer to figure out optimal strategies that lead to maximum rewards over time. Example: consider the process of teaching a dog tricks. When the dog performs a trick correctly, it receives a reward, treat, reinforcing the behavior. Similarly, in reinforcement learning, a computer might learn to play a game by receiving points, rewards for winning and losing points, penalties for losing. Everyday example: reinforcement learning explanation. In the context of a computer learning to play a game, reinforcement learning involves the computer receiving points for winning and losing points for losing over time. The computer adapts its strategies to maximize its points, much like a virtual pet learning to perform tasks. Example: imagine a computer playing a game where it receives points for successful moves or wins and loses points for unsuccessful moves or losses. Through reinforcement learning, the computer gradually discovers the best strategies to maximize its points, adapting its actions based on the feedback provided by the game environment. Learning through rewards and penalties. Explanation: reinforcement learning is centered around the concept of learning through the consequences of actions. Positive consequences in the form of rewards encourage the repetition of successful actions, while negative consequences in the form of penalties discourage undesirable actions. Example: think of reinforcement learning as a feedback loop. When the computer takes successful actions in a game, it receives rewards reinforcing those actions. Conversely, penalties for unsuccessful actions discourage the computer from repeating them. Goal-oriented learning. Explanation: reinforcement learning involves goal-oriented learning where the computer aims to maximize cumulative rewards over time. The agent learns to make decisions that lead to favorable outcomes based on the rewards associated with different actions. Example: consider a computer agent playing chess. The goal is to win the game, and the computer learns optimal moves by receiving positive reinforcement rewards for good moves that contribute to winning and negative reinforcement penalties for suboptimal moves. Exploration and exploitation. Explanation: in reinforcement learning, the computer must balance exploration, trying new actions to discover their effects, and exploitation, choosing known actions with high expected rewards. This balance is crucial for discovering optimal strategies. Example: think of the computer exploring different moves in a game. Initially, it may try various actions to understand their consequences. Over time, as it discovers successful moves, it shifts towards exploiting those actions to maximize rewards. Continuous adaptation. Explanation: reinforcement learning involves continuous adaptation to the environment. The computer learns and adjusts its strategies based on the feedback received through rewards and penalties, aiming to improve its overall performance. Example: imagine a computer playing a strategy game. It continually adapts its tactics based on the outcomes of its moves, learning from both successful and unsuccessful actions to enhance its overall gameplay. Application in gaming and decision making. Explanation: reinforcement learning has practical applications in gaming and decision making scenarios. It is used to train agents that can learn optimal strategies and make decisions based on the consequences of their actions. Example: consider training a virtual player in a video game. Through reinforcement learning, the virtual player learns to navigate the game environment, making decisions that lead to rewards, success, and avoiding actions that result in penalties, failure. In summary, reinforcement learning is a paradigm where a computer, like a trainable agent, learns by receiving rewards for good actions and penalties for bad ones. It is a dynamic and adaptive approach, finding applications in gaming, decision making, and scenarios where learning from interactions is essential. Why start with these concepts? Explanation: these concepts, supervised learning, unsupervised learning, and reinforcement learning, serve as the fundamental building blocks of machine learning. Each represents a distinct approach to learning from data: guided learning, exploration without explicit guidance, and learning through trial and error. Example: think of these concepts as the ABCs of machine learning. Supervised learning is like having a teacher guide you through examples. Unsupervised learning is akin to exploring on your own, and reinforcement learning involves learning through trial and error, much like a trial and error process of learning to play a musical instrument. Daily routine example explanation. Learning machine learning is likened to learning to play a musical instrument. Regular practice, such as working on small projects or solving simple machine learning problems, is emphasized as a crucial aspect of improvement and mastery. Example. Consider the process of learning to play a musical instrument where regular practice is essential for skill development. Similarly, in machine learning, engaging in daily practice through small projects or problem solving is key to enhancing proficiency. Foundation of machine learning explanation. Supervised learning, unsupervised learning, and reinforcement learning form the foundation of machine learning. They provide diverse approaches to extracting insights and making predictions from data, addressing a wide range of learning scenarios. Example. Think of these concepts as the cornerstone of your machine learning knowledge. They provide the necessary tools and methodologies for tackling various learning tasks, from guided learning with labeled data to autonomous exploration and trial and error learning. Guided learning, exploration, and trial and error. Explanation. Supervised learning involves guided learning with labeled examples. Unsupervised learning allows for exploration without predefined labels, and reinforcement learning entails learning through trial and error experiences. Example. Consider these approaches as different learning styles. Supervised learning is like following a teacher's guidance. Unsupervised learning is akin to self-exploration, and reinforcement learning involves learning from the consequences of actions, similar to trial and error. Versatility in learning scenarios. Explanation. These learning concepts are versatile and applicable to a wide range of learning scenarios. Depending on the nature of the data and the learning objectives, one or a combination of these approaches may be suitable. Example. Think of these concepts as versatile tools in your learning toolkit, depending on the task at hand, whether it's recognizing patterns in labeled data, discovering hidden structures, or optimizing decision making. Choosing the right learning approach is crucial. Continuous improvement through practice. Explanation. The analogy emphasizes the importance of regular practice in learning machine learning, drawing a parallel with the continuous practice required to master playing a musical instrument. Example. Just as regular practice is essential for mastering a musical instrument, consistent engagement with machine learning through small projects and problem solving is crucial for continuous improvement and skill enhancement. Progression and mastery. Explanation. Learning machine learning is portrayed as a journey of progression and mastery, where regular practice contributes to the development of skills and the ability to tackle more complex challenges. Example. Consider the journey of learning to play a musical instrument. With consistent practice, you progress from simple tunes to more complex compositions. Similarly, in machine learning, regular practice contributes to the ability to handle increasingly sophisticated tasks and projects. In summary, starting with supervised, unsupervised, and reinforcement learning concepts is foundational to understanding the diverse approaches within machine learning. Your analogy beautifully conveys the importance of regular practice as a key element in the journey of mastering machine learning. Much like mastering the skills of playing a musical instrument. Summary. Explanation. Machine learning is the art of teaching computers to learn and make decisions autonomously. It encompasses various approaches, with supervised learning involving guidance from a teacher, unsupervised learning exploring independently, and reinforcement learning through a system of rewards and penalties. Key points: supervised learning, analogy, similar to having a teacher guide you through examples. Characteristics: involves labeled training data with the algorithm, learning from explicit examples and their associated labels. Unsupervised learning, analogy, comparable to exploration without a teacher. Characteristics: involves unlabeled data and the algorithm autonomously discovers patterns and structures within the data. Reinforcement learning, analogy, likened to learning through rewards and penalties. Characteristics: involves in an agent making decisions to maximize cumulative rewards over time, learning through the consequences of its actions. Significance of starting with fundamentals, building blocks. These fundamental concepts serve as the building blocks of machine learning, providing diverse approaches to learning from data. Versatility. Each concept caters to different learning scenarios, from guided learning to autonomous exploration and trial and error learning. Strong base. Starting with these fundamentals establishes a robust foundation, enabling a deeper exploration of the dynamic and exciting world of machine learning. In summary, machine learning is a multifaceted field where the principles of supervised, unsupervised, and reinforcement learning lay the groundwork. Understanding these fundamentals equips individuals with the tools to navigate and delve deeper into the complexities of machine learning. Learning and exploring machine learning libraries and frameworks. What are libraries and frameworks? Think of libraries and frameworks as toolkits that make building things easier. They provide ready-made functions and structures so you don't have to start from scratch, like using pre-made logo blocks to build something cool. TensorFlow, your machine learning assistant. TensorFlow is like a smart assistant for machine learning. It helps you create and train machine learning models without writing everything from the ground up. It's like having a set of powerful tools that understand the language of machine learning. Everyday example, TensorFlow. If you want to teach a computer to recognize handwritten digits, TensorFlow provides pre-built functions that make it easier. It's like using a recipe to bake cookies instead of figuring out the ingredients and steps on your own. PyTorch, your creative canvas. PyTorch is like a creative canvas for machine learning. It gives you more flexibility and freedom to express your ideas. It's like having a blank canvas where you can paint your unique machine learning algorithms. Everyday example, PyTorch. If you have a new innovative idea for a machine learning model, PyTorch allows you to design and implement it in a way that suits your creativity. It's like being an artist who creates unique paintings. Why learn these tools? TensorFlow and PyTorch are like Swiss Army knives for machine learning. They save you time and effort, whether you are a beginner or an expert. Learning them is like becoming familiar with powerful tools that can make your machine learning projects more efficient and effective. Daily routine examples. Just like learning to use new app on your phone, spending some time regularly to understand and experiment with TensorFlow and PyTorch is beneficial. You might start with small projects like classifying images or predicting simple patterns. Summary. Machine learning libraries and frameworks are like toolkits that make building machine learning models easier. TensorFlow is like smart assistant with predefined tools, while PyTorch is like a creative canvas that allows more flexibility. Learning and exploring these tools is like getting comfortable with the tools or a craft, making your journey into machine learning more enjoyable and efficient. Understanding deep learning. What is deep learning? Deep learning is like teaching computers to think and learn in a way that resembles the human brain. It is the advanced side of machine learning where computers analyze and understand complex patterns. Neural networks, building blocks of deep learning. Neural networks are like virtual brains made up of interconnected neurons. Each neuron is like a tiny decision maker, and when you connect many of them, they work together to solve complex problems, just like a team of people with different skills collaborating. Everyday example, neural networks. Imagine you are deciding whether to go for a run. Your brain's neurons consider factors like weather, mood, and energy level. In a neural network, similar factors are considered to make decisions, like whether a picture contains a cat or a dog. Convolutional neural networks, CNNS, image detectives. CNNS are like special detectives for images. They analyze pictures in a way that understands patterns and features, just like you recognizing faces in a crowd. Everyday example, CNNS. When you look at a photo, your brain focuses on important details. CNNS do the same by identifying key features in images, like edges, shapes, and colors to recognize objects. Recurrent neural networks, RNNS, sequences and memory. RNNS are like storytellers with memory. They understand sequences, patterns, and context in data, just like you remembering the plot of a book as you read it. Everyday example, RNNS. If you are reading a sentence, your brain understands the meaning by considering the words that came before. RNNS works similarly, analyzing sequences of data like predicting the next word in a sentence or the next value in a time series. Why understand deep learning? Deep learning is like having a powerful tool for understanding and working with complex data. It's used in things like image recognition, language translation, and even self driving cars. Daily routine examples. Learning deep learning is like mastering a musical instrument. Start with the basics, practice regularly, and gradually take on more complex challenges. Summary. Deep learning is about training computers to understand complex patterns. Neural networks are like virtual brains. CNNS specialize in images, and RNNS understand sequences. Understanding deep learning is like gaining access to a set of advanced tools that can tackle intricate problems in the world of artificial intelligence. Neural networks, RNNS. Exploring natural language processing, NLP. What is natural language processing? NLP is like teaching computers to understand and work with human language. It's about bridging the gap between human communication and machine understanding. Everyday example, NLP. When you use voice commands on your phone, NLP is at work. It understands your spoken words and translate them into actions, like sending a text to or setting a reminder. Key applications of NLP. NLP is used in things like chatbots, language translation apps, and sentiment analysis. It helps computers make sense of text and interact with users in a more human like way. Daily routine example. Spending a few minutes a day chatting with a language learning app is like a fun workout for NLP. It helps you understand how computers interpret and respond to language. Exploring computer vision. What is computer vision? Computer vision is like giving machines the ability to see and interpret the visual world, similar to how humans use their eyes to understand their surroundings. Everyday example, computer vision. When you use facial recognition on your phone, computer vision is at play. It analyzes patterns in facial features to identify and unlock your device. Key applications of computer vision. Computer vision is used in self-driving cars to recognize objects and pedestrians, in medical imaging for diagnosis, and in augmented reality apps for interactive experiences. Daily routine example. Taking a moment to appreciate how your eyes recognize objects and shapes is like a mini lesson in computer vision. It helps You understand the challenges and possibilities in teaching machines to see. Why explore NLP and computer vision? NLP and computer vision are like two powerful senses for machines, understanding language and seeing the world. Mastering these areas opens doors to a wide range of applications in technology and artificial intelligence. Summary: NLP and computer vision are exciting frontier in machine learning. NLP helps machine understand and work with human language, while computer vision gives them the ability to see and interpret the visual world. Exploring these areas is like unlocking new dimensions in the capabilities of artificial intelligence. Studying model evaluation and metrics. What is model evaluation? Model evaluation is like giving grades to a student's performance. It's the process of assessing how well a machine learning model is performing on a given task. Why is evaluation important? Imagine you are a teacher checking homework. You want to know if your model students has learned and is performing well. Model evaluation helps us understanding how effective our machine learning algorithms are. Matrix, the grading system. Matrix are like the grades your teacher gives you. They quantify how well your model is doing. It's like getting an A for excellent performance or a C for average. Common matrix. Accuracy is like counting the number of correct answers out of all the questions. Precision is like focusing on how many of the selected items were relevant. Recall is like in ensuring you did not miss any important items. Everyday example. Model evaluation. Think of a spam filter in your email. If it marks important email as spam, low precision, you might miss important messages. If it lets too many spam emails through, low recall, it's not doing its job well. Balancing precision and recall is like finding the right mix for your spam filter to work effectively. Why study model evaluation? Model evaluation is like having a compass in a vast forest. It guides you to the best path. By understanding how well your model is performing, you can make improvements and choose the right algorithms for your task. Daily routine example. Checking the weather forecast is like a quick model evaluation. If the forecast says it will rain and it does, the model forecasting algorithm is doing well. If it consistently predicts sunny days when it rains, it needs improvement. Summary. Model evaluation is like assessing the performance of your machine learning models. Metrics act as grades, providing a quantitative measure of success. Understanding these metrics is crucial for fine-tuning your models, ensuring they perform well in real-world scenarios. Understanding version control. What is version control? Version control is like a time machine for your code. It helps you keep track of changes, go back to previous versions, and collaborate with others without chaos. Everyday example. Version control. Imagine you are writing a story on a computer. Each time you make a significant change, you save a new version of the document. Version control does the same for your code, ensuring you have a history of changes. Git, your time travel machine. Git is like a machine vent for version control. It allows you to create branches, alternate realities, make changes, and merge them back together, keeping your project organized. GitHub, sharing your story. GitHub is like a library where you store your stories. It's a platform that uses Git and allows multiple people to work on the same project. It's like having a shared space for your code. Everyday example. GitHub. Picture GitHub as a collaborative writing platform. You and your friends can work on the same story, make changes, and see who contributed what. It's like co-authoring a book with a group of people. Why use version control? Version control is like having a safety net. If something goes wrong, you can go back to a previous version It also makes collaboration easier by allowing multiple people to work on the same project without stepping on each other's toes. Daily routine example. Using version control is like backing up your important documents, regularly commit your changes and push them to the shared platform like GitHub to ensure your work is safe and accessible. Summary. Version control powered by tools like Git and platforms like GitHub is like a guardian for your code. It ensures you can travel back in time, collaborate seamlessly, and maintain order in your projects. Familiarizing yourself with these tools is a fundamental skill for any developer. Understanding model deployment. What is model deployment? Model deployment is like launching a ship. It's the process of taking your trained machine learning model and making it available for use in real world applications. Everyday example, model deployment. Think of deploying a model like putting a chef's recipe into action. You have perfected the recipe, trained the model, and now it's time to serve the dish. Use the model in applications. Integration into applications. Integrating a model into applications is like adding a new feature to a mobile app. It allows your model to be used seamlessly by people interacting with your application. Why deploy model? Deploying models is like bringing your creation to life. It allows others to benefit from the intelligence you have built into your machine learning model. Deployment platforms. Platforms like AWS, Azure, or Heroku are like stages for your model. They provide the infrastructure and environment needed to run your model at scale. Everyday example, deployment platforms. Imagine you have a food truck, your model, and you park it in different locations, deployment platforms to reach more people. Each platform provides a different audience for your delicious dishes, predictions for your model. Continuous monitoring. Continuous monitoring is like regularly checking the reviews of your restaurant. It ensures your model is performing well and helps you make improvements if needed. Daily routine examples. Updating your model in the deployed application is like releasing a software update for your app. It ensures your model stays accurate and relevant. Summary. Model deployment is the exciting phase where your machine learning model goes from being a project to being a useful tool in real world applications. Integrating it into applications and deploying on platforms is like putting your creation into the hands of users, allowing them to benefit from the intelligence you have built. Understanding deployment is a crucial step in the machine learning journey. Experimenting with cloud services for machine learning. What are cloud services? Cloud services are like renting powerful computers and services over the internet. Instead of having your own computer server, you can use resources from a cloud provider. Why use cloud services for machine learning? Imagine having access to a giant kitchen with all the ingredients and tools you need. Cloud services provide the infrastructure and tools for your machine learning experiments without having to set up and manage everything yourself. AWS, Google Cloud, Azure, the giant kitchens. AWS, Google Cloud, and Azure are like massive kitchens equipped with state-of-the-art appliances. They offer a variety of services, including machine learning tools that you can use for your projects. Everyday example, cloud services. If you are a chef, developer, cloud services are like having a team of assistants who handle everything from chopping vegetables to cleaning up. You can focus on cooking, developing without worrying about the details. Machine learning services. Cloud platforms provide pre-built machine learning services like image recognition, natural language processing, and predictive analytics. It's like having specialized chefs in your kitchen who are experts in different cuisine. Everyday example, machine learning services. If you want to analyze customer reviews to understand sentiments, a cloud platform's NLP service is like a talented chef who quickly reads and interprets reviews, saving you time and effort. Cost and scalability. Using cloud services is like paying for the ingredients and space you use in a shared kitchen. You can scale up or down based on your needs, just like adjusting the size of your kitchen based on the number of guests. Daily routine example. Allocating resources on a cloud platform is like deciding how much space you need in your kitchen each day. You can choose to use a few burners for a small project or the entire kitchen for a big experiment. Summary. Experimenting with cloud services for machine learning is like having access to a tech kitchen with all the tools and ingredients you need. AWS, Google Cloud, and Azure offer a range of services that simplify the machine learning process, making it easier to experiment, scale, and deploy your projects. Understanding data pre-processing. What is data pre-processing? Data pre-processing is like preparing ingredients before cooking. It involves cleaning, organizing, and transforming raw data into a format that machine learning models can effectively learn from. Everyday example, data pre-processing. Imagine you are making a fruit salad. Before tossing everything together, you wash, peel, and cut the fruits. Data pre-processing is similar. It's the step where you clean and prepare your data before you feeding it to a machine learning model. Steps in data pre-processing. Cleaning data. Cleaning is like removing bruised or spoiled fruits from your salad. In data terms, it involves handling missing values, correcting errors, and addressing inconsistencies. Handling missing values. Missing values are like having some ingredients missing in your recipe. Data pre-processing involves deciding whether to remove those instances or fill in the missing values based on logical methods. Scaling and normalization. Scaling is like adjusting the size of your fruits to make them uniform. In data, it ensures that numerical features are on a similar scale, preventing one feature from dominating the others. Encoding categorical data. Encoding is like representing fruits by numbers. In data, it involves converting categorical variables like fruit types into numerical form so that the machine learning model can understand them. Feature engineering. Feature engineering is like creating a new fruit salad recipe. It involves creating new features from existing ones to provide more relevant information to the model. Removing outliers. Outliers are like adding a giant watermelon to your small fruit salad. They can skew the results. Data pre-processing includes identifying and handling outliers appropriately. Why is data pre-processing important? Data pre-processing is like ensuring your kitchen is clean and your ingredients are fresh before cooking. It ensures that your machine learning model does not get confused by messy or incomplete data, leading to better results. Everyday example, importance of data pre-processing. If you are making a smoothie and don't remove the seeds from a watermelon, it might affect the taste. Similarly, if you don't pre-process your data, it might introduce unwanted noise and impact the performance of your machine learning model. Daily routine example. Incorporating data pre-processing into your routine is like washing your hands before cooking. It becomes a habit that ensures that success of your machine learning projects. Summary. Data pre-processing is a crucial step in machine learning, ensuring that your data is clean, organized, and ready for analysis. It's like preparing the ingredients for a recipe, making sure that the machine learning model can learn effectively from the data you provide. understanding and mastering data pre-processing is key to building robust and accurate machine learning models. Optimizing and fine-tuning models. What is model optimization? Model optimization is like adjusting the settings on your camera to capture the perfect shot. It involves fine-tuning various aspects of your machine learning model to improve its performance. Everyday example, model optimization. Imagine you are baking cookies. Model optimization is like tweaking the recipe, adjusting the temperature, baking time, and ingredient proportions to get the best tasting cookies. Hyperparameter tuning. Hyperparameter tuning is like finding the right combination of ingredients and their quantities for your recipe. In machine learning, hyperparameters are external configurations that influence the learning process, and tuning involves finding the best values for them. Grid search. Grid search is like trying different combinations of ingredients systematically. In machine learning, it involves testing various combinations of hyperparameter values to find the most effective set. Random search. Random search is likely experimenting with new ingredient combinations. Instead of trying every possible combination, random search explores different sets of hyperparameters randomly, which can be more efficient in some cases. Model evaluation matrix. Model evaluation matrix are like tester for your cookies. They help you assess how well your model is performing. Common metrics include accuracy, precision, recall, and F1 score. Why optimize models? Optimizing models is like perfecting your recipe for the best results. It ensures that your machine learning model performs well on the task at hand, leading to more accurate predictions. Everyday example. Why optimize models? If your cookie recipe is too sweet, you might adjust the sugar quantity. Similarly, if your model's predictions are not accurate, optimization helps you adjust hyperparameters to improve performance. Learning rate ingredient descent. Learning rate is like the speed at which you mix ingredients. Too fast and you might spill. Too slow and it takes forever. Optimizing the learning rate in machine learning is crucial for efficient model training. Daily routine example. Experimenting with different hyperparameter values during your daily machine learning routine is like tweaking your cookie recipe over time until you get the perfect batch. Summary. Optimizing and fine-tuning machine learning models is like adjusting a recipe to make it perfect. Hyperparameter tuning using techniques like grid search or random search ensures that your model performs at its best. Just as a chef refines a recipe, a data scientist fine-tune models to achieve optimal results in their machine learning projects. Experimenting with ensemble learning. What is ensemble learning? Ensemble learning is like forming a team of experts to make a collective decision. Instead of relying on one model, ensemble methods use multiple models and combine their predictions for better accuracy and robustness. Everyday example. Ensemble learning. Think of ensemble learning as creating a panel of food critics to judge your dishes. Each critic has their preferences, but collectively their judgment gives a more reliable evaluation. Bagging, bootstrap aggregating. Bagging is like having multiple chefs prepare the same dish independently. In machine learning, it involves training multiple models on different subsets of the data and averaging or voting their predictions. Everyday example, bagging. If you are unsure which route to take to work, you might ask different friends for their advice. Bagging does a similar thing by combining predictions from models trained on different subsets of the data to make a more robust decision. Boosting. Boosting is like learning from your mistakes. It focuses on improving areas where the model struggles. In each iteration, it assigns more weight to misclassified instances, helping the model learn better over time. Everyday example boosting. If you are learning a new language and struggling with certain words, you might spend more time practicing those. Boosting does a similar thing, giving more attention to challenging instances during training. Random forest, a bagging ensemble. Random forest is like having a group of chefs collaborate to create a menu. It's a bagging ensemble method that builds multiple decision trees, each trained on a different subset of data and combines their predictions. Gradient boosting, a boosting ensemble. Gradient boosting is like refining a skill step by step. It builds decision trees sequentially, each correcting the errors of the previous one. The final prediction is a combination of these trees. Why use ensemble learning? Ensemble learning is like having a diverse team with complementary skills. It reduces the risk of relying on a single model and often leads to more accurate predictions. Everyday example. Why use ensemble learning? Just as a diverse group of friends might provide more well rounded advice, ensemble learning combines the strengths of different models to create a more robust and reliable solution. Daily routine example. Incorporating ensemble learning into your machine learning routine is like having a reliable group of advisors for your projects. It becomes a valuable tool in your toolkit for improving model performance. Summary. Ensemble learning is a powerful approach in machine learning, leveraging the collective wisdom of multiple models to enhance accuracy and robustness. Bagging and boosting are two popular techniques that bring diversity and learning from mistakes into the modeling process. Just as collaboration enhances decision making in various scenarios, ensemble learning strengthens the predictive capabilities of machine learning models. Reinforcement learning explained. What is reinforcement learning? Reinforcement learning is like training a dog. The agent, dog or artificial intelligence, learns to make decisions by interacting with an environment, receiving feedback, rewards, or penalties based on its actions. Everyday example reinforcement learning. Consider teaching a dog a new trick. When the dog performs the trick correctly, you reward it with a treat. Similarly, in reinforcement learning, the artificial intelligence receives positive reinforcement when it makes the right decisions. Key components agent, the learning or decision maker, dog or artificial intelligence environment, the external system with which the agent interacts, actions, possible moves or decisions the agent can make, rewards, penalties, feedback the agent receives based on its actions. Algorithms in reinforcement learning, Q learning. Q learning is like trying different actions and figuring out which one lead to the best outcomes over time. The agent maintains a table, Q table, to guide decision making. Deep Q network, DQN. DQN is like upgrading from a traditional camera to a high-tech one. It uses neural networks to approximate the Q values, making it suitable for complex environments. Policy gradient methods. Policy gradient methods are like adjusting your strategy based on the success or failure of your actions. The agent directly learns a policy, a strategy to choose actions. Applications of reinforcement learning, game playing. Reinforcement learning is like training an artificial intelligence to play chess or Go. The agent learns by playing against itself or other opponents, improving its strategies over time. Robotics. In robotics, reinforcement learning is like teaching a robot to perform tasks by rewarding successful movements and correcting errors. Autonomous vehicle. Reinforcement learning is like training a self-driving car. The artificial intelligence learns to make decisions by navigating and adapting to different road conditions. Recommendation systems. In recommendation systems, reinforcement learning is like adjusting recommendations based on user interactions and feedback. Why use reinforcement learning for decision making? Reinforcement learning is like giving artificial intelligence the ability to learn from experience. It's particularly useful in scenarios where decision making involves sequential actions and feedback. Everyday example, decision making. If you are playing a video game, you make decisions based on the current situation, adapting your strategy as the game progresses. Reinforcement learning allows artificial intelligence to make dynamic decisions in a similar way. Daily routine example. Incorporating reinforcement learning into your machine learning routine is like adding a decision making module to your artificial intelligence projects, enabling them to adapt and improve through interaction with their environment. Summary. Reinforcement learning is a dynamic paradigm where artificial intelligence learns to make decisions by interacting with its environment and receiving feedback. Algorithms like Q-learning and DQN, applied in applications such as game playing, robotics, and autonomous vehicles, showcase the power of this approach in decision-making scenarios. Exploring reinforcement learning is like giving your artificial intelligence the ability to learn, adapt, and excel in tasks that involve sequential decision making. Mastering feature engineering. What is feature engineering? Feature engineering is like sculpting raw materials into a work of art. In machine learning, it involves transforming raw data into a set of features that captures the most relevant information for the model. Everyday example, feature engineering. Imagine you are taking a photo. Feature engineering is like adjusting the lighting, framing, and focus to highlight the essential elements and create a stunning image. Key aspects of feature engineering. Creating new features. This is like adding ingredients to a recipe. By combining or transforming existing features, you create new ones that may provide more meaningful information to the model. Handling missing data. Dealing with missing data is like completing a puzzle. You might fill in missing value based on averages or other logical methods to ensure the model has all the recipes it needs. Encoding categorical variables. Encoding like translating between languages, converting categorical variables into numerical representations helps the model understand and learn from them. Scaling and normalization. Scaling is like bringing all your ingredients to the same unit of measurement. It ensures that numerical features are on a similar scale, preventing one feature from dominating others. Binding and discretization. Binding is like categorizing age groups. It can turn continuous data into discrete groups, making it easier for the model to identify patterns. Why master feature engineering? Feature engineering is like tuning an instrument before a performance. It enhances the quality of the data, allowing the model to extract more relevant information and make better predictions. Everyday example, importance of feature engineering. Just as choosing the right lens for a camera shot can make a significant difference, feature engineering ensures that the data presented to the model is optimized for effective learning. Domain knowledge. Understanding the domain is like knowing the theme of painting. It helps you decide which features are most relevant and how they should be transformed to enhance the model's understanding. Continuous iteration. Feature engineering is not a one-time task. It's an ongoing process like refining a recipe based on feedback. Continuously iterating on features improves model performance over time. Everyday example, continuous iteration. If you are a chef, you might adjust the seasoning of a dish based on customer feedback. Similarly, feature engineering involves refining features based on the model's performance and feedback. Daily routine example, incorporating feature engineering into your machine learning routine is like sharpening your tools before starting a project. It becomes a fundamental step in creating models that perform at their best. Summary: mastering feature engineering is an art that involves transforming raw data into a format that enhances model performance. Like crafting a masterpiece, selecting, creating, and refining features is crucial for building accurate and effective machine learning models. Understanding the nuances of feature engineering is key to extracting meaningful insights from data and making your models shine. Exploring explainability and interpretability. What is explainability and interpretability? Explainability and interpretability are like having a clear recipe for your dish. They refer to the ability to understand and explain the decisions made by a machine learning model in a human understandable way. Everyday example: explainability. Think of explainability as a chef explaining the ingredients and steps behind a dish. It helps stakeholders, including non-technical users, understand how and why the model makes certain predictions. Techniques for explainability. Feature importance. Feature importance is like highlighting the key ingredients in a recipe. It helps understand which features have the most impact on the model's decisions. Partial dependence plots. Partial dependence plots are like showcasing the influence of one ingredient on the overall taste. They demonstrate how changing one feature affects the model's predictions. Local interpretable model agnostic explanations LIME. LIME is like getting a second opinion on your recipe. It creates a locally faithful model around a specific prediction, making it easier to understand why the model made that particular decision. Shapley values. Shapley values are like attributing credit to each ingredient for the final taste. They assign a value to each feature, indicating its contribution to a particular predictions. Why focus on explainability and interpretability? Explainability is like reading the nutritional information on food packaging. It builds trust, helps identify biases, and ensures that decisions made by the model align with human expectations. Everyday example: importance of explainability. Just as you might question a chef about an expected flavor in a dish, stakeholders may question model predictions. Explainability provides the answer needed to build confidence in the model. Techniques for model interpretability. Simpler models. Using simpler models is like having a recipe with fewer ingredients. Simpler models are often more interpretable and easier to understand. Decision trees. Decision trees are like a flow chart for making a dish. They provide a step-by-step guide to understand how the model reaches a decision. Model agnostic approaches. Model agnostic approaches are like having a universal cookbook. They work with any machine learning model, providing a consistent way to interpret predictions. Applications in critical areas. In critical applications like healthcare or finance, explainability is like having clear documentation for medical procedures. It ensures that decisions made by the model are understandable and can be trusted. Ethical considerations. Understanding the decisions of a model is crucial for ensuring fairness. Explainability helps identify and address biases, making models more ethical and accountable. Daily routine example. Incorporating explainability into your machine learning routine is like adding a clear set of instructions to your code. It becomes a standard practice to ensure that models are transparent and understandable. Summary: explainability and interpretability are integral aspects of machine learning, especially in critical applications. Techniques like feature importance, partial dependence plots, and model agnostic approaches provide the means to understand and communicate the decision made by models. Just as a chef explains the artistry behind a dish, machine learning practitioners aim to make their models transparent, trustworthy, and interpretable. Understanding transfer learning. What is transfer learning? Transfer learning is like starting a new recipe with a well-seasoned pot. Instead of training a model from scratch, you leverage knowledge gained from solving one problem to tackle different but related problem. Everyday example, transfer learning. Imagine you have mastered making a tomato sauce for pasta. When trying a new recipe, you might use the same sauce as a base, modifying it slightly. Transfer learning does a similar thing, using knowledge gained from one task to improve performance on a related task. Key concepts, pre-trained models. Pre-trained models are like having a collection of well-tested spice blends. They are models trained on massive datasets for tasks like image classification, natural language processing, or object detection. Fine tuning. Fine tuning is like adjusting the seasoning of a pre-made sauce to suit your taste. It involves taking a pre-trained model and training it further on your specific task or dataset. Domain adaptation. Domain adaptation is like tweaking the recipe to match regional preferences. It adjusts the model to perform well on a target domain even if the data is slightly different from the original pre-trained data. Why use transfer learning? Transfer learning is like having a head start in a cooking competition. It saves time, computational resources, and often lead to better performance on new tasks. Everyday example, why use transfer learning? Just as a seasoned chef might reuse well-crafted sauce in multiple dishes, transfer learning allows you to reuse knowledge gained from the task to excel in related tasks. Techniques for transfer learning. Feature extraction. Feature extraction is like using specific spices from a pyramid blend. It involves taking the knowledge captured in the pre-trained model's early layers and applying it to a new task. Fine-tuning top layers. Fine-tuning the top layers is like adjusting the final seasoning of a dish. It focuses on training the last layers of the pre-trained model on the new task while keeping the early layers fixed. Pre-trained embeddings. Pre-trained embeddings are like using versatile sauce as a base for different recipes. In natural language processing, for instance, you might use pre-trained word embeddings in your specific language-related task. Applications of transfer learning. Transfer learning is like using a proven recipe as a foundation for variations. It finds applications in image recognition, natural language processing, and many other domains where pre-trained models can jumpstart new projects. Daily routine example. Incorporating transfer learning into your machine learning routine is like having a collection of trusted ingredients that you can adapt to different recipes. It becomes a strategic approach to efficiently tackle various tasks. Summary. Transfer learning is a powerful technique that allows practitioners to leverage knowledge gained from pre-trained models to improve performance on new tasks, whether fine-tuning specific layers or using pre-trained embeddings. Transfer learning streamlines the machine learning process and facilitate better results in various applications. Just as a seasoned chef builds on existing recipe to create new culinary delights, transfer learning enables data scientists to efficiently address a variety of machine learning challenges. Developing soft skills in machine learning. Why soft skills matters? Soft skills are like the presentation and serving skills of a chef. In machine learning, they complement technical expertise, enabling effective collaboration, understanding, and communication. Communication skills. Clear and concise communication. It's like explaining a recipe in simple terms. Clearly communicate complex machine learning concepts, algorithms, and results in a way that is understandable to both technical and non-technical audience. Active listening. Active listening is like understanding a customer's preferences. Pay attention to the needs and feedback of team members, stakeholders, and end users to ensure that your machine learning solutions meet their expectations. Effective documentation. It's like creating a recipe book. Document your code models and processes comprehensively, making it easy for others to understand and use your work. Teamwork, collaborative problem solving. Teamwork is like working together to create a delightful meal. Collaborate with colleagues to solve challenges, share ideas, and leverage diverse perspectives for more robust machine learning solutions. Project management. Project management is like coordinating a kitchen, organize and prioritize tasks, set realistic timelines, and ensure smooth collaboration among team members to achieve project goals. Conveying complex concepts, storytelling. Storytelling is like presenting a dish creatively. Use stories and real world examples to illustrate complex machine learning concepts, making team more relatable to non-technical stakeholders. Visualizations. Visualizations are like presenting a visually appealing dish. Use charts, graphs, and diagrams to represent data and model outcomes, facilitating understanding for those who may not be familiar with technical details. Tailored communication. It's like adjusting the level of spice in a dish. Tailor your communication style to suit your audience, whether they are fellow data scientists, managers, or clients. Continuous improvement. Seek feedback. Seeking feedback is like getting reviews for a new dish. Regularly seek feedback on your communication and collaboration skills and use it to continually improve. Training and workshops. Attend training sessions and workshops. Just like a chef attending culinary classes, develop your soft skills through targeted learning opportunities focused on communication, teamwork, and effective presentations. Daily routine example. Incorporating soft skills development into your routine is like dedicating time for recipe refinement. Regularly practice communication, collaboration, and conveying complex concepts to hone these skills. Summary. Soft skills are the essential ingredients that complement technical experience in machine learning, developing clear communication, effective teamwork, and the ability to convey complex concepts to diverse audiences enhances your overall effectiveness as a machine learning professional. Just as a chef skillfully interacts with the kitchen staff and explains dishes to customers, mastering soft skills allows you to navigate the collaborative and communicative aspects of the machine learning field successfully. Considering machine learning specializations, computer vision, description. Computer vision is like teaching machines to interpret and understand visual information from the world. It involves tasks such as image recognition, object detection, and image segmentation. Applications. Facial recognition, autonomous vehicles, medical image analysis, and augmented reality are examples of applications in computer vision. Skills to develop. Image processing, convolutional neural networks, CNNs, object detection algorithms, and familiarity with image datasets. Natural language processing, NLP. Description. Natural language processing is like enabling machines to understand, interpret, and generate human language. It involves tasks such as text classification, sentiment analysis, and machine translation. Applications. Chatbots, language translation services, sentiment analysis tools, and text summarization are common applications in natural language processing. Skills to develop. Text pre-processing, sequence models, that is recurrent neural networks and transformers, word embeddings, and working with large language datasets. Reinforcement learning. Description. Reinforcement learning is like teaching machines to make decisions through trial and error. It involves an agent interacting with an environment, learning from rewards or penalties, and optimizing its behavior. Applications. Game playing, that is AlphaGo, robotic control, recommendation systems, and Personalized content delivery are examples of applications in reinforcement learning. Skills to develop: Markov decision processes, policy gradients, Q-learning, and experience with simulation environments for training agents. Time series analysis. Description: Time series analysis is like understanding and predicting data that changes over time. It involves analyzing temporal patterns, detecting trends, and making predictions based on historical data. Applications: stock market forecasting, energy consumption prediction, weather forecasting, and anomaly detection in time series data. Skills to develop: time series modeling, auto regressive integrated moving average ARIMA, long short term memory LSTM, networks, and handling temporal datasets. Recommender systems. Description: Recommender systems are like personal shopping assistants, suggesting items or content based on user preferences. They involve collaborative filtering, content-based filtering, and hybrid methods. Applications: product recommendations on e-commerce platforms, movie or music recommendations, and personalized content suggestions on streaming services. Skills to develop: collaborative filtering algorithms, content-based filtering, matrix factorization, and understanding user item interactions. Healthcare informatics. Description: Healthcare informatics is like using machine learning to improve healthcare outcomes. It involves tasks such as disease prediction, medical image analysis, and personalized treatment recommendations. Applications: disease diagnosis, medical imaging analysis, patient risk prediction, and drug discovery are examples of applications in healthcare informatics. Skills to develop: medical image analysis techniques, predictive modeling for patient outcomes, and knowledge of healthcare datasets and regulations. Autonomous systems. Description: Autonomous systems involve making machines operate independently and make decisions without human intervention. It includes robotics, autonomous vehicles, and drone technology. Applications: self-driving cars, drones for surveillance, and autonomous robots for warehouse management are examples of applications in autonomous systems. Skills to develop: robotics, sensor fusion, path planning algorithms, and understanding the challenges of real-world deployment. Explainable AI (XAI). Description: Explainable artificial intelligence focuses on making machine learning models more transparent and understandable. It involves techniques to interpret and explain model predictions. Applications: critical applications where understanding model decisions is crucial, such as healthcare diagnostics and financial decision making. Skills to develop: interpretability techniques, model agnostic explanation, and understanding ethical. Edge computing and IoT. Description: Edge computing and the Internet of Things IoT involves deploying machine learning models on edge devices, reducing the need for centralized processing. It includes optimizing models for resource-constrained environments. Applications: smart home devices, industrial IoT applications, and real-time analysis on edge devices. Skills to develop: model optimization for edge devices, knowledge of edge computing frameworks, and handling data from IoT sensors. Quantum machine learning. Description: Quantum machine learning explores the intersection of quantum computing and machine learning. It involves leveraging quantum computing principles for solving complex machine learning problems. Applications: solving optimization problems, quantum enhanced machine learning algorithms, and simulations of quantum systems. Learning database management for machine learning. What is database management? Database management is like organizing and maintaining a recipe book. It involves storing, retrieving, updating, and managing large amounts of data in a structured and efficient manner. everyday example, database management. Imagine you are a chef managing a kitchen with various ingredients. Database management is like organizing your ingredients, keeping track of quantities, and ensuring everything is easily accessible. Key concepts. Relational databases. Relational databases are like well-organized recipe books with tables. They store data in structured tables with relationships, facilitating efficient data retrieval and updates. SQL, Structured Query Language. SQL is like the language of a recipe book. It allows you to communicate with databases, perform queries, and manipulate data. Data modeling. Data modeling is like designing a menu. It involves structuring data in a way that represents real-world entities and their relationships, ensuring efficiency in data storage and retrieval. Indexing. Indexing is like creating an index for your recipe book. It speeds up data retrieval by creating pointers to specific row in a table. Working with databases in machine learning, data collection and storage. It's like sourcing and storing ingredients, collect and store datasets in databases, ensuring they are well organized and easily accessible for machine learning tasks. Data pre-processing. Pre-processing is like preparing ingredients before cooking. Use SQL queries and database functions to clean, transform, and pre-process data for machine learning models. Feature engineering. Feature engineering is like creating unique recipes, utilize SQL and database functions to create new features, aggregate data, and extract relevant information for machine learning tasks. Model training and testing. Model training is like cooking and testing is like tasting your dish. Efficiently retrieve, training and testing data from databases to develop and evaluate machine learning models. Database types. Relational databases, that is MySQL, PostgreSQL. These are like traditional recipe books with organized tables and relationships. They are suitable for structured data and complex queries. NoSQL databases, that is MongoDB, Cassandra. NoSQL databases are like unconventional recipe storage, suitable for unstructured or semi-structured data. They provide flexibility and scalability. In-memory databases, that is Redis, Memcached. In-memory databases are like having all your ingredients on the kitchen counter for quick access. They store data in RAM, providing high-speed data retrieval. Data security. It's like securing your recipe book from unauthorized access. Implement security measures, including access controls and encryption, to protect sensitive machine learning datasets. Scaling databases. Scaling databases is like adapting your kitchen for larger operations. Explore techniques such as sharding and replication to scale databases horizontally or vertically as data volume grows. Database optimization. Database optimization is like fine-tuning your cooking process, optimize queries, create efficient indexes, and analyze query execution plans for better performance. Data integration. Data integration is like combining ingredients from different suppliers, integrate data from multiple sources into a centralized database for comprehensive analysis and machine learning. Daily routine example. Incorporating database management into your machine learning routine is like maintaining an organized kitchen. Regularly update, clean, and optimize your databases to ensure a smooth workflow. Summary. Learning database management is essential for efficiently handling and processing large datasets in machine learning. Just as a chef organizes ingredients for seamless cooking, mastering database management ensures that data is well structured, accessible, and optimized for machine learning tasks. Understanding relational databases, SQL, data modeling, and optimization techniques enhances your ability to work with data effectively and drive valuable insights through machine learning. Exploring edge computing for machine learning. What is edge computing? Edge computing is like having a mini kitchen right where you are cooking. Instead of sending all data to a centralized server, edge devices process data locally, reducing latency and bandwidth usage. Everyday example, edge computing. Imagine you are a chef cooking in a food truck. Edge computing is like having a kitchen on the truck, enabling you to prepare dishes without relying on a distant central kitchen. Key concepts, edge devices. Edge devices are like your cooking utensils in the food truck. These are devices like smartphones, IoT devices, or even edge servers that perform computation locally. Low latency. Low latency is like serving dishes quickly to your customers. Edge computing minimizes the time it takes for data to travel between the device and the processing center, ensuring faster responses. Resource constraints. Resource constraints are like having a limited set of ingredients. Edge devices often have limited processing power, memory, and energy, making optimization crucial. Deploying machine learning models on edge devices. Model optimization. Model optimization is like creating a simplified version of your recipe for a food truck. Make machine learning models smaller, efficient, and suitable for deployment on resource constrained devices. Quantization. Quantization is like condensing your ingredients. It involves reducing the precision of numeric values in the model, making it more lightweight. Pruning. Pruning is like trimming excess ingredients. Remove unnecessary parts of the model to reduce its size without compromising performance. On-device inference. On-device inference is like cooking directly on the food truck. Perform model inference, predictions on the edge device without relying on a central server. Edge computing frameworks. TensorFlow Lite. TensorFlow Lite is like having a special set of cooking utensils for the food truck. It's a framework for deploying machine learning models on edge devices with a focus on optimization. ONNX runtime. ONNX runtime is like a versatile cooking tool that can handle various tasks on the food truck. It supports the deployment of models in the Open Neural Network Exchange ONNX format. Edge TPU, Tensor Processing Unit. Edge TPU is like having a dedicated cooking appliance on the food truck. It's a hardware accelerator designed by Google for accelerating machine learning workloads on the edge. Edge computing applications, smart cameras. Smart cameras are like having eyes on the food truck. They use edge computing to process images locally for applications like surveillance or object detection. IoT devices. IoT devices are like sensors in the food truck collecting data on temperature, humidity, etc. Edge computing enables real-time analysis of this data without relying on a central server. Autonomous systems. Autonomous systems are like having a robot chef on the food truck. Edge computing allows the device to make decisions locally, crucial for real-time responses in autonomous vehicles or robots. Connectivity considerations. Intermittent connectivity. Intermittent connectivity is like driving the food truck through areas with poor signals. Edge computing ensures that the device can operate and make decisions even when the connection is unstable. Bandwidth efficiency. Bandwidth efficiency is like optimizing your route to avoid traffic. Edge computing reduces the need to send large amounts of data to a central server, conserving bandwidth. Security and privacy. On-device processing. On-device processing is like preparing a dish without revealing the recipe. Edge computing enhances privacy by processing sensitive data locally without sending it to a central server. Secure deployment. Secure deployment is like locking the doors of the food truck. Ensure that the edge device and its deployed models have robust security measures to protect against potential threats. Daily routine examples. Incorporating edge computing into your machine learning routine is like adapting your cooking techniques for different kitchens. Regularly optimize models for edge deployment and stay updated on edge computing frameworks. Summary. Edge computing is a game changer in machine learning, especially for resource constrained environments. Just as a food truck chef optimizes recipes for on the go cooking, machine learning practitioners need to optimize models for deployment on edge devices. Understanding model quantization, pruning, and deploying with frameworks like TensorFlow, Lite, or ONNX runtime empowers you to bring the power of machine learning to the edge efficiently. Staying ethical and responsible in machine learning. Understanding ethical considerations. Description. Understanding ethical considerations is like having a code of ethics in your kitchen. Be aware of potential biases, fairness issues, and transparency concerns in machine learning models and applications. Key steps. Stay informed about ethical guidelines and principles in machine learning. Consider the potential impact of your work on different individuals and communities. Reflect on the ethical implications of algorithmic decisions. Address bias and fairness. Description. Addressing bias and ensuring fairness is like balancing flavors in a dish. Strive to identify and mitigate biases in your machine learning models to ensure equitable outcomes. Key steps. Regularly assess your datasets for potential biases. Use techniques such as resampling, reweighting, or adversarial training to address bias. Implement fairness-aware algorithms to ensure equitable treatment across different groups. Transparent model development. Description. Transparency in model development is like sharing the recipe with your diners. Make your machine learning models transparent and understandable to users, stakeholders, and the broader community. Key steps. Document your model development process, including data sources and pre-processing steps. Explain model decisions using interpretable techniques and tools. Communicate potential limitations and uncertainties associated with the model. Data privacy protection. Description. Protecting data privacy is like safeguarding the secret ingredients of your recipe. Ensure that sensitive and personal information is handled responsibly and in compliance with privacy regulations. Key steps. Anonymize or pseudonymize sensitive data to minimize the risk of identification. Implement privacy preserving techniques such as federated learning or differential privacy. Comply with data protection laws and regulations relevant to your work. Informed consent. Description. Informed consent is like having your diner aware of the ingredients in a dish. Obtain consent from individuals when collecting and using their data for machine learning purposes. Key steps. Clearly communicate the purpose of data collection and usage to users. Provide options for individuals to opt in or opt out of data collection. Respect user preferences and choices regarding their data. Regular ethical audits. Description. Regular ethical audits are like health inspections for your kitchen. Conduct periodic assessments of your machine learning models and applications to identify and address ethical concerns. Key steps. Establish a framework for ethical audits, including criteria for evaluation. Involve diverse stakeholders, including ethicists and representatives from impacted communities. Iterative and improve your models based on the findings of ethical audits. Addressing unintended consequences. Description. Addressing unintended consequences is like adjusting the seasoning in a dish. Be vigilant about potential negative impacts of your models and take corrective measures. Key steps. Monitor the real world impact of your machine learning applications. Be responsive to feedback and reports of unintended consequences. Iteratively improve models to minimize harmful effects. Ethical decision making framework. Description. Having an ethical decision making framework is like having a set of guiding principles in your kitchen. Develop and follow a framework that helps you make ethical decisions throughout the machine learning lifecycle. Key steps. Consider the ethical implications at each stage of model development. Involve stakeholders in ethical decision-making processes. Seek external input and ethical reviews for complex or high-impact projects. Community engagement. Description. Community engagement is like interacting with your diners to understand their preferences. Engage with the broader community, including those affected by your models, to gather insights and feedback. Key steps. Participate in discussions and forums. Focuses on machine learning ethics. Collaborate with advocacy groups and organizations working on responsible artificial intelligence. Seek public input on high impact decisions that may affect communities. Continuous learning. Description. Continuous learning is like staying updated on culinary trends. Stay informed about emerging ethical considerations, best practices, and evolving regulations in machine learning. Key steps. Read research papers, attend conferences, and participate in webinars on machine learning ethics. Join online communities and forums dedicated to ethical artificial intelligence discussions. Take courses or training programs that focus on responsible artificial intelligence and ethics. Daily routine example. Incorporate ethical considerations into your daily routine, just like checking the quality of your ingredients. Reflect on the potential ethical implications of your work and take proactive steps to address them. Summary. Staying ethical and responsible in machine learning is a foundational principle for building trustworthy and sustainable models. Just as chefs prioritize the quality and integrity of their dishes, machine learning practitioners must prioritize fairness, transparency, and ethical considerations. Continuously evaluate the impact of your work, address biases, and engage with the community to ensure that machine learning technologies contribute positively to society. Embracing continuous experimentation in machine learning. Openness to exploration. Description. Openness to exploration is like trying out new ingredients in your recipes. Be willing to explore different algorithms, techniques, and methodologies in machine learning. Key steps. Stay curious and explore diverse machine learning algorithms beyond the ones you are familiar with. Experiment with different hyperparameters, settings, and optimization techniques. Read research papers and stay informed about the latest advancements in the field. Rapid prototyping. Description. Rapid prototyping is like creating a quick draft of your recipe. Develop prototype models swiftly to test initial hypotheses and assess the viability of different approaches. Key steps. Use frameworks like TensorFlow or PyTorch to quickly prototype machine learning models. Iterate through different architectures and feature engineering strategies. Focus on obtaining quick feedback to refine your models rapidly. A/B testing. Description. A/B testing is like comparing two versions of your dish to see which one is preferred. Apply A/B testing principles to compare the performance of different machine learning models or algorithms. Key steps. Split your dataset into two groups and apply different algorithms or approaches. Evaluate and compare the performance matrix to identify the more effective solutions. Iterate based on the results to improve model performance. Hyperparameter tuning. Description. Hyperparameter tuning is like adjusting the seasoning in your dish. Experiment with different hyperparameter values to optimize the performance of your machine learning models. Key steps. Conduct systematic experiments to find the optimal values of hyperparameters. Utilize tools like grid search or random search for hyperparameter tuning. Continuously refine hyperparameters based on model performance. Ensemble methods. Description. Ensemble methods are like combining different ingredients for a harmonious flavor. Experiment with ensemble techniques such as bagging or boosting to improve model robustness. Key steps. Build multiple models using different algorithms or variation of the same algorithm. Combine their predictions through techniques like bagging, that is random forest, or boosting, that is AdaBoost. Assess the ensemble models performance compared to individual models. Transfer learning. Description. Transfer learning is like using a pre-made sauce as a base for your dish. Experiment with transfer learning techniques to leverage knowledge from pre-trained models for new tasks. Key steps. Fine-tune pre-trained models on your specific dataset or task. Explore different pre-trained models and architectures. Evaluate the benefits of transfer learning in terms of model performance and training time. Feature engineering. Description. Feature engineering is like adding unique ingredients to enhance your dish. Experiment with creating new features from existing data to improve model performance. Key steps. Explore different feature extraction techniques and transformations. Conduct through analysis to identify relevant features for your specific task. Iterate on feature engineering based on model performance and insights gained. Model interpretability techniques. Description. Model interpretability techniques are like understanding the secret behind a dish. Experiment with interpretability tools and methods to gain insights into how your machine learning models make decisions. Key steps. Use techniques like SHAP, Shapley Additive Explanations, or LIME, Local Interpretable Model Agnostic Explanations, for model interpretability. Experiment with visualizations and matrix to understand feature importance. Iteratively refine your models based on interpretability insights. Experiment tracking and documentation. Description. Experiment tracking is like keeping a detailed record of your cooking process. Implement systems for tracking experiments, recording results, and documenting lesson learned. Key steps. Use tools like MLflow or TensorBoard to log and track experiments. Document changes in algorithms, hyperparameters, and experimental outcomes. Regularly review and reflect on past experiments to inform future decisions. Collaborative experimentation. Description. Collaborative experimentation is like having a group of chefs contribute to a recipe, collaborate with colleagues, participate in machine learning communities, and share insights to foster a culture of collective learning. Key steps. Share your experiments, findings, and challenges with colleagues and peers. Participate in collaborative projects or competitions on platforms like Kaggle. Learn from others' experiments and incorporate best practices. Learning from failures in machine learning. Embrace a growth mindset. Description. Embracing a growth mindset is like considering each failure as a step towards improvement. Understand that challenges and failures are inherent in the learning process. Key steps. View challenges as opportunities to learn and grow. Cultivate a positive attitude towards setbacks, seeing them as temporary and solvable. Recognize that intelligence and skills can be developed over time through effort and learning. Analyze and understand failures. Description. Analyzing failure is like investigating why a recipe did not turn out as expected. Take the time to understand why a machine learning model failed and identify the root causes. Key steps: conduct a thorough analysis of model performance, examining metrics and results. Identify potential issues in data quality, feature engineering, or model architecture. Seek feedback from peers, mentors, or online communities to gain diverse perspectives. Document and reflect. Description: documenting and reflecting on failures is like keeping a chef's logbook. Document the details of failed experiments and reflect on the decisions made during the process. Key steps: maintain a record of experiments, including algorithms, hyperparameters, and outcomes. Reflect on the decisions made at each stage of the machine learning pipeline. Consider what could be improved or done differently in subsequent attempts. Iterate and experiment again. Description: iterating and experimenting again is like refining a recipe after feedback. Take the lessons learned from failures and use them to iteratively improve your machine learning models. Key steps: adjust hyperparameters, algorithms, or pre-processing techniques based on insights from failures. Experiment with new approaches or incorporate feedback received. Continuously iterate on your models and solutions. Fail fast, learn faster. Description: failing fast is like quickly identifying what does not work, allowing you to learn faster. Don't hesitate to test hypotheses and fail early in the process to accelerate the learning curve. Key steps: set up experiments with clear hypotheses and expectations. Monitor and evaluate experiments regularly to identify failures promptly. Use failures as opportunities to pivot and try alternative approaches. Share failures with the community. Description: sharing failure with the community is like discussing culinary mishaps with fellow chefs. Openly share your experiences, challenges, and lessons learned with the machine learning community. Key steps: participate in discussions on platforms like forums, social media, or collaborative projects. Share your failures in a constructive manner, highlighting key takeaways. Learn from the experiences of others who have faced similar challenges. Seek feedback and mentorship. Description: seeking feedback and mentorship is like consulting with an experienced chef. Reach out to peers, mentors, or experts in the field to gain valuable insights and guidance. Key steps: share your failed experiments with mentors or experienced practitioners. Seek specific feedback on areas where improvements can be made. Use mentorship to refine your approach and decision-making processes. Develop resilience. Description: developing resilience is like being able to handle kitchen mishaps with composure. Cultivate resilience in the face of failures, recognizing that setbacks are a natural part of the learning journey. Key steps: build the capacity to bounce back from failures with a positive mindset. Focus on learning from failures rather than dwelling on setbacks. Develop coping strategies to navigate challenges in a constructive manner. Experiment in safe environments. Description: experimenting in safe environments is like trying out new recipes in a controlled setting. Choose environments like sandbox, projects, or personal experiments where the impact of failures is limited. Key steps: start with small-scale experiments to test hypotheses without significant consequences. Gradually increase complexity as you gain confidence and experience. Use safe environments to explore unconventional ideas without fear of major repercussions. Celebrate learning opportunities. Description: celebrating learning opportunities is like acknowledging the lessons gained from a challenging recipe. Recognize that failures provide valuable learning experiences and celebrate the opportunity to refine your skills. Key steps: Shift the perspective from failure to learning opportunity. Acknowledge and celebrate the insights gained from each failure. Share success stories that emerged from overcoming challenges and setbacks. Daily routine example. Incorporate failure analysis into your daily routine, just like reviewing and adjusting your cooking techniques. Regularly assess the outcomes of experiments, identify areas for improvement, and use failures as stepping stones towards mastery. Summary. Learning from failures is an integral part of the machine learning journey. Just as chefs refine their recipes through trial and error, machine learning practitioners gain expertise by analyzing and iterating on field experiments. Embrace failures as opportunities to learn, document insights, and continuously improve your skills and approaches. The ability to learn from setbacks is a hallmark of a resilient and successful machine learning practitioner. Exploring time series analysis in machine learning. Definition of time series. Description. A time series is a sequence of data points collected or recorded in a chronological order, typically at equally spaced intervals. Time series data can be found in various domains such as finance, economics, weather forecasting, and more. Key concepts. Each data point is associated with a specific timestamp. Time series data exhibits temporal dependencies and trends. Unique challenges in time series analysis. Description. Time series analysis presents distinct challenges compared to traditional machine learning tasks due to the temporal nature of the data. Key challenges. Temporal dependencies. Data points are not independent. They are influenced by previous observations. Seasonality. Patterns may exhibit recurring cycles or seasonality. Trend detection. Identifying long-term trends in the data is essential. Temporal anomalies. Detecting unusual events or anomalies over time. Time series analysis techniques. Description. Various techniques are employed to analyze and model time series data. Key techniques. Descriptive analysis. Examine basic statistical properties, visualize trends, and identify patterns. Decomposition. Separate a time series into its constituent components such as trend, seasonality, and residual. Autogressive integrated moving average, ARIMA, a popular method for modeling and forecasting time series data. Exponential smoothing, ETS, a family of methods that assigns exponentially decreasing weights to past observations. Seasonal trend decomposition using Loess, STL, decomposes time series into trend, seasonality, and remainder using local regression. Feature engineering for time series. Description. Feature engineering is crucial in time series analysis to extract relevant information for modeling. Key steps. Lag features include lagged values of the target variable as features. Rolling statistics. Computer rolling mean, median, or other statistics over a specified windows. Time-based features. Extract temporal features like day of the week, month, or quarter. Exogenous variables. Integrate external factors that might influence the time series. Seasonal decomposition of time series, STL. Description. STL decomposition is a technique to break down a time series into trend, seasonality, and residual components. Key steps. Decompose the time series using local regression. Identify and analyze the trend, seasonality, and residual components separately. Model each component independently for forecasting. ARIMA modeling. Description. ARIMA, autoregressive integrated moving average, is a popular method for time series forecasting. Key concepts. Autoregressive, AR components. Past values of the series influence future values. Integrated component. Differencing the series to make it stationary. Moving average, MA components. Past forecast errors influence future values. Profit time series forecasting. Description. Profit is an open source forecasting tool designed for time series with daily observations that display patterns on different time scales. Key features: handles missing data and outliers, allow for the inclusion of custom seasonalities and holidays, provides uncertainty intervals for forecasts. Anomaly detection in the time series description. Detecting anomalies is critical in identifying unusual patterns or events in time series data. Key techniques: threshold based methods define thresholds for abnormal values. Statistical methods use statistical measures like z-scores to identify deviations. Machine learning approaches employ supervised or unsupervised algorithms to detect anomalies. Time series cross validation description. Additional cross validation methods are adapted for time series data to account for temporal dependencies. Key methods: walk forward validation, train the model on past data and validate on the next time step. Expanding window validation, incrementally include more data for training in each iteration. Daily routine example: incorporate time series analysis into your daily routine, like inspecting the freshness of ingredients. Regularly analyze and model time series data, adjusting your approach based on patterns and challenges encountered. Summary: time series analysis is a specialized domain within machine learning, focusing on data points ordered over time, recognizing the unique challenges, employing appropriate techniques, and staying mindful of temporal dependencies are key to effectively analyzing and forecasting time series data, whether dealing with financial data, weather patterns, or other time-dependent phenomena. Mastering time series analysis enhances your ability to extract meaningful insights and make accurate predictions. Cloud service models description. Cloud providers offer various service models allowing users to choose the level of control over their computing resources. Service models: infrastructure as a service (IaaS). User manage and control the virtualized infrastructure, including operating systems and applications. Platform as a service (PaaS) provides a platform with development tools and services, abstracting underlying infrastructure details. Software as a service (SaaS) offers fully managed software applications accessible over the internet. Cloud deployment models description. Cloud providers offer different deployment models to cater to diverse user needs. Deployment models: public cloud. Services are delivered over the internet and shared among multiple users. Private cloud. Services are hosted on a private network, often within an organization. Hybrid cloud combines elements of both public and private clouds for flexibility. Benefits of cloud computing for machine learning description. Cloud computing provides several advantages for machine learning practitioners and organizations. Key benefits: scalability, easily scale computing resources up or down based on demand. Cost efficiency, pay only for the resources consumed, avoiding upfront infrastructure costs. Flexibility and agility, quickly deploy and experiment with machine learning models and solutions. Global reach, access computing resources from anywhere with an internet connection. Cloud computing platforms for machine learning description. Major cloud providers offer dedicated machine learning services and tools. Key platforms: Amazon Web Services provides a comprehensive set of machine learning services, including SageMaker for model building and hosting. Microsoft Azure offers Azure machine learning for end-to-end machine learning workflows. Google Cloud Platform (GCP) feature artificial intelligence platform for building, deploying, and managing machine learning models. IBM Cloud provides Watson Studio for collaborative data science and machine learning. Cloud-based machine learning services. Description. Cloud providers offer specialized services tailored for machine learning workflows. Key services: data storage. Services like Amazon S3, Azure BLOB storage, or Google Cloud Storage for storing large data sets. Computer instances, virtual machine for training machine learning models, that is AWS EC2, Azure virtual machines, machine learning platforms. Services like AWS SageMaker, Azure Machine Learning, and Google Artificial Intelligence Platform for end-to-end machine learning workflows. Serverless computing, execute code without managing infrastructure, that is AWS lambda, Azure functions. Steps to deploy machine learning on the cloud. Description. Deploying machine learning on the cloud involves several key steps. Deployment steps. Data preparation. Prepare and store data sets in cloud storage. Model training. Utilize cloud-based compute instances for training machine learning models. Model deployment. Deploy models on cloud platforms for inference. Scalability testing. Assess and adjust resources based on workload demands. Monitoring and management. Implement monitoring tools for model performance and resource utilization. Security and compliance. Description. Cloud providers prioritize security and compliance to protect user data. Security measures. Identity and access management, IAM. Control access to resources and services. Data encryption. Encrypt data at rest and in transit. Compliance certifications. Cloud providers adhere to industry-specific compliance standards. Daily routine example. Incorporate cloud computing into your daily routine, much like accessing a virtual kitchen with all the necessary tools. Use cloud platforms to experiment, train, and deploy machine learning models seamlessly. Summary. Cloud computing is a foundational technology that empowers machine learning practitioners with scalable and flexible infrastructure. Understanding the key concepts, benefits, and available services from major cloud providers allows individuals and organizations to leverage cloud computing for efficient and powerful machine learning solutions. Whether deploying models, conducting experiments, or managing large datasets, cloud computing provides the necessary resources to meet the dynamic demands of machine learning workflows. AutoML, automated machine learning. Definition of AutoML. Description. AutoML refers to the use of automated tools and processes to streamline the machine learning workflow, from data preparation and feature engineering to model selection and deployment. Key concepts. Automated model selection. Tools automatically choose the most suitable algorithm for a given task. Hyperparameter tuning. Automatically search for optimal hyperparameter values. Feature engineering. Automated techniques for selecting or transforming features. Model deployment. Streamlining the employment process for machine learning models. Benefits of AutoML. AutoML offers several advantages, particularly in terms of efficiency, accessibility, and democratizing machine learning. Key benefits: time efficiency. Reduces the time required for manual tasks in the machine learning pipeline. Accessibility allows individuals without extensive machine learning expertise to build and deploy models. Resource efficiency optimizes resource utilization by automating repetitive tasks. Model performance can potentially discover high performing models by exploring a wide range of possibilities. AutoML tools and platforms. Description. Various AutoML tools and platforms are available, catering to different needs and expertise levels. Key platforms Google AutoML provide a suite of AutoML tools for VN, natural language, and tabular data. Microsoft Azure AutoML offers AutoML capabilities for building machine learning models on Azure. H2.0 Artificial Intelligence provides an open source platform with AutoML capabilities. DataRobot, an enterprise grade AutoML platform with a user friendly interface. Steps in AutoML workflow. Description: the AutoML workflow typically involves several key steps to automate the machine learning process. Workflow steps: data preparation, automated handling of missing values, data pre-processing and feature engineering. Algorithm selection, automatically choose the most appropriate algorithm for a given task. Hyperparameter tuning, searches for optimal hyperparameter values for the selected algorithm. Ensemble methods, incorporates ensemble techniques to improve model performance.